Hello, welcome back everyone. For some reason this room's a bit sort of emptier than yesterday at 9 a.m. Don't know why. Nothing to do with a Welsh bar at sort of 2 o'clock in the morning. A little bit of housekeeping just to kick us off. If the evacuation alarm sounds, you need to exit this building via stairs, not lifts. Assemble out the front of the Intercontinental on the corner of 1 or 2 Grey Street. And if an earthquake happens, drop and get some cover. If you're not from New Zealand, you've never been in an earthquake and you don't know how bad it is, just watch the Kiwis. If they look pretty good, then just do nothing. Cool. So unfortunately, due to sort of the times we live in, our first speaker today has got a little bit of a virus or a cold. So he's actually done a video recording of his talk. So we'll beam that in a moment. I'd like to welcome to the kind of virtual stage, Dwayne DeWitt from Cisco, and he's going to be talking about peering fabric design.
Good morning and happy Friday. My name is Dwayne DeWitt, pronounced Divits, like the hole in the grass that you leave when you swing a golf club. Speaking of golf, I hope some of you at least are looking forward to the championship this weekend. I certainly am. This morning we're going to talk about the intelligent peering fabric. I'll go through some high-level concepts, we'll go through some use cases for the fabric, and then speak a bit about the technology. So in terms of high-level concepts, the peering design leverages high-density, environmentally efficient edge routers, leaf-spine topology, and features delivered through an advanced network OS to solve the needs of service and content providers. Also included as part of the peering design are ways to monitor the health and operational status of the peering edge, and through automation integration assist providers in automating peer configuration as well as validation. The guidance is to place peering or content provider cache nodes as close to traffic consumers as possible. This obviously reduces the capacity required on long-haul backbone networks, but also improves the quality of experience for users by reducing the latency to content sources. The design utilizes a fabric separating the network functions into separate physical layers connected via an external fabric running over standard Ethernet. In many typical SP peering deployments, a traditional 2-node setup is used where providers vertically upgrade nodes to support the higher capacity needs of the network. Some may employ technologies such as back-to-back or multi-chassis clusters in order to support more connections while keeping what seems like a low operational footprint. However, the failures and operational issues occurring in these types of systems are typically difficult to troubleshoot and repair. They also require lengthy planning and time frames for software upgrades. So we suggest a horizontally scalable distributed peering fabric, the end result being more deterministic interface and node failures. Minimizing the loss of peering capacity is very important for both ingress-heavy service providers as well as egress-heavy content providers. The loss of local peering capacity means traffic must ingress or egress through suboptimal network points. So making a conscious decision to spread peer connections, even to the same peer, across multiple edge nodes helps increase resiliency and limit traffic affecting network events. Now on to some of the use cases for the fabric. A traditional internet exchange design uses 1 or 2 large modular systems terminating all of the peering connections. In many cases, since service providers are constrained on space and power, they use a collapsed design where the minimal set of peering nodes not only terminate peer connections, but also provide services and core connectivity to the location. The peering fabric uses best-of-breed high-density, low-footprint hardware, requiring much less space than older generation modular systems. Due to the superior space efficiency, there is no longer a limitation of using just a pair of nodes for these functions. Peers can be distributed across a number of devices to increase resiliency and decrease collateral impact when failures occur. In some cases, there may be peering facilities within close geographic proximity, which need to integrate into a single fabric. This may happen where there are multiple third-party facilities close together, each with unique peers that you need to connect to. There may also be multiple independent peering facilities within a small geography, and in these cases, connecting remote leaves to a larger peering fabric can be done using optical transport or longer-range grey optics. In order to drive greater network efficiency, content sources should be placed as close to the end destination as possible. Traditional service providers have heavy inbound traffic from content providers delivering OTT video. Providers may also be providing their own IP video to on-net and off-net destinations via a CDN. Peering and internal CDN equipment can be placed within a localized peer or content delivery center connected via common peering fabric. In these cases, the spine nodes connect directly to the metro core to enable delivery to the region or metro. An evolution to localized metro peering is to interconnect the spine peering nodes directly to aggregation or access nodes for metro-wide peering. The main driver for direct interconnection is minimizing the number of router and transport interfaces that traffic needs to pass through. High-density optical muxponders along with flexible photonic ROADM architectures can help make the most efficient use of the metro fiber assets. In order to serve traffic as close to consumer endpoints as possible, a provider may construct a peering edge attached to an edge or central data center. As gateway functions in the network become virtualized for applications such as virtual provider edge, virtual CPE, and now mobile 5G, the need to attach internet peering to the service provider data center becomes more important. The peering fabric can interconnect to the data center via the service provider core or with the spine nodes as leads to the data center spine. These would act as traditional border routers in the data center design. We'll now talk a bit about the functions within the fabric. The peering leaf is the node physically connected to external peers. Peers could be aggregation routers or third-party CDN nodes. In a deconstructed design such as this, the leaf is analogous to a line card in a modular chassis solution, and so leaf nodes can be added as capacity needs grow. The peering fabric spine is an aggregation for the leaves, and it also physically connects to the rest of the provider network. The provider network could refer to a metro core in the case of localized peering, a backbone core in relation to internet exchange peering, or a data center spine layer in the case of data center peering. In order to maximize resiliency in the fabric, each leaf node is connected to each spine. While the design here shows 3 leaves and 2 spines, there could be any number of leaf and spine nodes scaling horizontally to keep up with traffic and interface growth. Leaf nodes are not connected to each other. The spine nodes provide the capacity for any traffic between the leaves. The spine nodes are also not connected to each other. Capacity of the peering fabric is scaled horizontally. The uplink capacity from the leaf to the spine will be determined by an appropriate oversubscription factor. The leaf spine architecture of the fabric connects each leaf to each spine with equal capacity. In a steady state operation, traffic is balanced between the spine and the leaf in both directions, maximizing total capacity. The entropy in peering traffic generally ensures equal distribution between either ECMP paths or bundle interface members in the egress direction. Often overlooked when connecting to internet peers is determining a strategy to maximize efficiency and resiliency within a local peering instance. Oftentimes, a peer is connected to a single peering node, even when 2 nodes exist for ease of configuration and coordination with the peering partner. However, with minimal additional configuration and administration assisted by automation, even single peers can be spread across multiple edge peering nodes. Ideally, within a peering fabric, a peer is connected to each leaf in the fabric. In cases where this cannot be done, the provider should use capacity planning processes to balance peers and transit connections across the multiple leaves in the fabric. The added resiliency leads to greater efficiency when failures do happen, with less reliance on peering capacity further away from the destination. The peering fabric design introduces a simplified control plane built on IPv4 or IPv6 with segment routing. In the distributed design, network functions are separated. Peer termination happens on the peer fabric leaf nodes. The peer fabric leaf is connected directly to peers via traditional eBGP. And BFD can be used for fault detection, obviously if both ends of the link support it. Each eBGP peer will utilize segment routing egress path engineering to enable traffic engineering to the peer from elsewhere on the provider network. Peering fabric spine aggregation nodes are responsible for core connectivity and perform more advanced label edge routing functions. The spine routers use equal cost multipathing to balance traffic between leaf routers and are responsible for forwarding within the fabric and to the rest of the provider network. Each spine acts as a label edge router incorporated into the control plane of the core network. The spine, or otherwise some virtual route reflectors, reflect learned peer routes from the leaf nodes to the rest of the network. The segment routing control plane supports several traffic engineering capabilities, egress path engineering to a specific peer interface, a leaf node, or a spine is supported. We also introduced the abstract peering concept, where spine nodes utilize a next hop address bound to an Anycast SR SID to allow traffic engineering on a per peering center basis. Leaf to spine uses widely deployed standard routing protocols. ISIS is the typical IGP protocol within the peering fabric. Each spine is configured with the same ISIS level 1 area. In the case where OSPF is being used as an IGP, the leaf nodes will reside in an OSPF not so stubby area. The peering fabric IGP is segment routing enabled, with the loopback of each leaf assigned a globally unique SR node SID. Each leaf also has an iBGP session to each route reflector to distribute its learned eBGP routes upstream and learn routes from elsewhere on the provider network. If a provider is distributing routes from leaf to leaf or from another peering location to local leaves, it's important to enable the BGP best path external feature to ensure the spine has the routing information to accelerate reconvergence if it loses the more preferred path. Egress peer engineering will be enabled for eBGP peering connections so that each peer or peer interface connected to the leaf is directly addressable by its adjacency peer SID from anywhere on the service provider network. Adjacency peer SID information is currently not carried in the IGP of the network, so if it's being used, it's recommended to distribute this information using BGP LS to all of the controllers that are creating paths to the leaf destinations. Each spine node will be configured with iBGP multipath, so traffic is load balanced to leaf nodes and increased resiliency in the case of peer failure. On reception of a BGP withdrawal update for a multipath route, traffic loss is minimized as the existing valid route is still programmed into the FIB. The spine nodes will participate in the global core control plane and act as the gateway between the peering fabric and the rest of the service provider network. In order to create a more scalable and programmatic fabric, It's recommended to use segment routing across the core infrastructure. And then slow peer detection should be turned on. Slow peers are those who are slow to receive and process inbound BGP updates and acknowledge those to the sender. If the slow peer is participating in the same update group as other peers, this can slow down the update process for all of the peers. Unfortunately, that's all the time that we have this morning for the topic. For any further information, there's a great repository, xrdocs.io, or otherwise reach out to me. I'm available on LinkedIn to answer any questions that you might have. There's a lot more information to cover around telemetry, around traffic engineering and security, which we obviously couldn't cover in this time frame. So thank you for your time and hoping to hear from you.
Thank you, Dwayne. So theoretically, we've actually got Dwayne online to take questions. Yes, we do. So if anyone's got any questions in the room, please put your hand up and we'll try using the wonders of technology to... Oh, down the back there, Richard.
Kia ora morena, Joel here. In my past life as a network engineer with NZNOG, the architecture you just presented was pretty much what we've been selling in for many years. I guess one of the questions I had just from in the field experience is like, I see you're putting an ISAS in the middle and or OSPF, as you sort of said. My experience is that just seems to complicate things for no real gain. And I know you mentioned segment routing within the spine leaf associations. I guess the question is, why do you see the need to add another protocol rather than just using IBGP and eBGP to the edges? Like, what's your rationale?
So the main intent of using segment routing is to simplify the traffic engineering techniques to be able to direct traffic to a specific location, a specific node, or even a specific egress interface connecting to a peer. So leveraging egress path engineering is a lot simpler than trying to deal with MED and communities and the typical BGP techniques.
Any other questions out there? No, that's us. Thank you very much, Dwayne. So we're 5 minutes ahead of schedule for our next talk, which is a virtual talk coming in from Finland. Is Timo ready, AV people, do we know, or?
I am ready.
Oh, great, cool. So yes, apologies to Timo, because when we scheduled NZNOG back in January, I think this is going to be about 10 p.m. local time for him due to daylight saving. So now I think it's around about midnight or so for him, so he's staying up late for us. So I'd like to welcome Timo from Red Hat. As I said, he's beaming in from Finland. He's going to talk about cloud technologies that can be used with RAN and open source. Anyway, over to Timo.
Thank you very much. I'm going to share my screen. I hope you see it good. Yes, so it's a little bit past midnight, very early Friday morning, but it's okay. Actually, I was requesting a travel from Finland to New Zealand to give 30 minutes talk, but that did not go well. So I'm here at home. Yeah, so my name is Timo Jokio. I'm Chief Technologist at the Red Hat Telecom Media and Entertainment Organization in EMEA. And I'm ex-Nokia, of course, being a Finnish engineer, but also ex-Huawei and ex-Samsung before coming to Red Hat about 8 years ago when Red Hat started the NFV journey with the virtualization platform and all these things. But today I'm going to talk about radio access networks, or how cloud technologies and open source technologies play into disaggregated radio access. So this is the overall agenda. There's quite a lot of material, but I'm sure I'm going to handle that in 30 minutes. Let's go into it. So this is a kind of a mandatory slide we always need to present. It describes our development model, which we call open source upstream first, which is a unique development model still. So what that really means is that, first of all, most of our software developers, I don't know, maybe 75–80% of our software developers, they work in the middle, in the open source projects, directly in the open source projects. So they don't work in internal Red Hat project, but open source project together with our customers and partners, and very much with our competitors, sharing sharing experience and sharing code and ideas and all these things. And from that, we downstream the community releases to both hand sides of this slide, and then we test, we fix bugs and push everything back to open source communities, upstream communities, and then create our supported products, which are on the both hand sides of this slide. And why we call it upstream first is an important thing to understand. So when our customers or partners, when they request a new feature into our product, any of the products, we can commit to that product only when the upstream community has agreed that this feature will be included into some future community releases. So, and once that is agreed with the communities, then we can commit to our customers that, yeah, that feature will be in release X of our product. That's why it's called upstream first. So we kind of not control fully our product roadmaps. We always need to socialize and negotiate the feature development with the upstream community leaders, which we do. And we have been doing that for 25 years or even more. Now going to telco. So Red Hat corporate overall strategy is a horizontal cloud platform in all of the places. And we telco people at Red Hat, we use this diagram or this kind of diagram to show that in telecom domain, in telecom networking domain, we are pushing for a horizontal cloud platform in all of the places. Starting from the right-hand side, which is OSS BSS domain, very much IT-like applications, going towards left to the core network, mobile core, fixed core, and enterprise or private networks. And then on the left-hand side, the access, fixed and radio access. And today we talk about radio access. And the platform, in our case, it's nowadays called OpenShift container platform based on Kubernetes, which is a industry agreed container orchestration open source project. That platform can be running on edge, regional cloud, private cloud, public cloud, even on Amazon and Microsoft and Google, and then giving the kind of a uniform experience to the application developers and applications, no matter where they are running. So just a quick view. Now, short overview of disaggregated RAN. I'm sure everybody knows this well, but I'm kind of picky on few things like terminology, which I come very quickly. So this is what's happening, has been happening in RAN space. On the left-hand side is the RAN functional split, which is a 3GPP specification or standard, splitting the base station into 3-entity model, which I show in a minute. And then on the right-hand side, on that model, functional split model, the RAN cloudification can be introduced. And that's, of course, something what Red Hat is highly interested on, to provide a software platform to disaggregate the hardware and software, not only all entities, but the baseband unit entities, which I will show soon. And these are the organizations working on the RAN domain. There are others, but these are the three main organizations. 3GPP obviously is a standardization authority in mobile networks, has been since 3G. 2G was specified by ETSI, but since 3G it has been 3GPP. And based on the disaggregation model or functional split model, a couple of things happened. O-RAN Alliance was one thing. What was happening, there was a couple of other organizations which merged into O-RAN Alliance some time ago. So O-RAN Alliance takes the 3GPP functional split specification and split model and start adding interfaces and architectural specifications on how the RAN should be built based on certain software entities and standard interfaces between the entities, sort of complementing what 3GPP has done. And then Telecom Infra Project at the bottom of the slide is a very practical organization having many working groups, not just RAN, but also core and many others. But on my opinion, the most valuable thing Telecom Infra Project is doing is running their, I think, 17 community labs globally, testing the kind of interoperability testing between these entities specified by 3GPP and O-RAN Alliance. Very important labs. Now, I'm very picky on these terms, what industry is using related to disaggregated RAN. And it's very confusing, I have to say, and I try to clarify it. I'm not sure if I'm successful, but if you look at the Venn diagram on the right-hand side, that's kind of a big picture of what is happening in the RAN industry. So the Open RAN is an industry movement, and now I have to specify it's an Open RAN with the space in between Open and RAN, because there's another Open RAN which is a 0.2 on left-hand side, which is Open RAN without space, and those two things are completely different, confusing. But the Venn diagram maybe or hopefully shows what's happening. So the Open RAN movement includes Open RAN Telecom Infra Project Group. It includes O-RAN Alliance and work of O-RAN Alliance. And then on the far right is the virtual RAN, which might not be having any open interfaces. It just virtualizes the BBO functionalities. And then C-RAN is kind of a subset of vRAN, bringing in cloud-native technologies into the picture. So this is highly confusing. I mean, these terms are highly confusing, and there are many people and companies have written white papers and blogs to try to clarify it, and this is my attempt to try to do that. Again, not sure if I'm successful or not, but this is how it looks like. So the traditional RAN is a high-level diagram of what it means and what are the main entities related to functional split and Open RAN. So this is how it looks like. And when we split that based on 3GPP functional split model or disaggregation model, the base station looks like this. So there is a radio unit on the left-hand side. And then there's a distributed unit, and then there's a centralized unit. And the traditional or classical baseband unit is split between DU and CU, roughly. And this model really is not Open RAN because there is, for example, proprietary interface between radio unit and distributed unit in this diagram. Of course, there's a 3GPP mid-hole interface, but it's quite typical that the DU and CU anyway come from one vendor. So this is basically a single RAN vendor model, although they can still apply third-party software platform on DU and CU or hosting DU and CU entities, and that's why I call it Cloud RAN or vRAN, virtual RAN. So the platform is hosting or separating hardware and software in the UNCU domain. And that's one of the models where Red Hat plays very actively, providing OpenShift container platform to replace the third-party platform in my diagram. So very important for us. The next model is the same, but adding the first and most important, in my opinion, most important ORAN Alliance interface, which is open fronthaul between RU and DU. And based on ORAN Alliance nomenclature, they call these entities, or they add O- in front of RU, DU, and CU, just to show that they are more or less ORAN Alliance compliant RAN workloads. Otherwise, this diagram is exactly the same as the previous, only open fronthaul is introduced. And this cannot be called ORAN Alliance compliant because it only has open fronthaul, no more or less. So I call this partially compliant to ORAN Alliance. Again, the third-party platform is there, and it doesn't need to be ORAN Alliance third-party platform or container platform. In this case, it is not. And third model is introducing the O-Cloud, which is an ORAN Alliance name for the cloud platform in their terminology or nomenclature. This is a very high-level picture of the whole thing, but the cloud platform, the red box can be exactly the same in all these three models I showed. Now the last one of diagram on this model is a kind of a complete ORAN Alliance RAN implementation, and the block diagram itself, it is from one of the ORAN Alliance white papers, and the only thing I have added is are all those dashed lines for 4G LTE radio line and 5G new radio line, and then O-Cloud hosting ODU, OCU on both LTE and 5G, and then near real-time RIC, and then another O-Cloud or the same O-Cloud, depends, hosting service management and orchestration, and then the other RIC. And as you can see on this diagram, it's quite complex, and if you really build a multi-vendor ORAN Alliance RAN, there can be many vendors because in theory, all of these blocks can come from different vendors. I don't think that's ever going to happen, but in theory, yes. So having a fully ORAN Alliance compliant RAN is still some time away. But the previous models I showed, partially compliant with open fronthaul, that's reality today. And then single RAN vendor disaggregated RAN is reality today, but the fully ORAN Alliance compliant RAN is not happening right now because of many reasons. Many of these interfaces are not even specified yet, or the work is ongoing and they are not referenceable at this point, but it's going to happen. Now, I'll go through a few technical things, what needs to happen from the cloud platform point of view, remembering that we as Red Hat, we only provide open source cloud platform and automation tools. We don't provide any workloads, not for RAN, not for anything else. So all these features I'm going to talk about, they are really focusing on what we need to do to make OpenShift container platform credible for disaggregated RAN or Open RAN. And these are the three most important things we have had to do for distributed unit. Centralized unit is kind of easy. It's a little bit smaller footprint edge cloud or aggregation cloud, but the distributed unit is challenging because that connects directly to radio unit. So many RAN vendors RAN workload vendors, they do need real-time execution environment for their DU workload to have a very strict, low latency, deterministic scheduling for their workload, and that has to happen even on cloud platform domain, not just host operating system domain, but the whole cloud platform domain. And we have not just we, but the industry have very good idea what those numbers should be. What is the acceptable maximum scheduling latency, so that all RAN vendors are happy. And that number is, the number itself doesn't tell too much, but the number is around 10 microseconds or 8 microseconds, and that number cannot be exceeded anywhere. And we have many references that that's the correct number. The other one is very interesting, again related to cloud platform, is radio access network timing and synchronization with precision time protocol and all these grandmasters and border clocks and anything you might have. And on purpose, we have been presenting our work in several international conferences during last 1.5 years. Of course, virtually first, but the last one was in-person International Timing and Synchronization Forum in UK last fall, just to show that the RAN timing and synchronization with the precision time protocol today, Sync-E is coming, but PTP today we can achieve the required 1.5 microsecond timing error using open source software and commercial off-the-shelf hardware, NIC cards and all these things. So that's very important, and it has been surprise internally at Red Hat that we need to do that into our platform, but there's a reason for that, and I'm going to talk about that in a minute. And the third very important must-have feature is to integrate hardware accelerators into distributed unit in form of FPGA or SmartNIC or GPU or whatever you might have to allow or to give access to the RAN to the DU workload, access to the hardware acceleration, and then connect that to radio unit for forward error correction and many other purposes. And interestingly enough, we who need to integrate the hardware accelerator into the system, we don't need the hardware accelerator at all ourselves, but we just need to integrate that and provide a good and seamless way for the workloads to access the hardware accelerators. Then there is a bunch of other requirements to RAN, and this is an example, of course not a complete set of requirements which need to be there. And these requirements also apply to centralized unit, not just distributed unit, but centralized unit as well. But also these apply to many other non-RAN related edge use cases, which this same platform is managing as well, enterprise edge use cases or any other use cases. And these are very, very typical things which need to be present in the platform when deploying an edge use case, and not just RAN, but any edge use case. So just quickly on the left-hand side, 3 different models to tackle the low footprint requirement on the edge side, on general edge side, but also the radio edge side. So the basic model of the Kubernetes platform, not just OpenShift, but the Kubernetes model is to have 3 servers, which is an upper left-hand side. So 3 physical servers, and you have supervisors and workers on those 3 servers. So that's a kind of a standard model of Kubernetes cluster. And the worker nodes, of course, can be then extended and added more and more and more. And the middle one on the left-hand side is, we call it single node OpenShift, which means that there's a single physical server and the whole OpenShift cluster is installed on a single physical server because of footprint reasons. So that's what we have, and that's what many or few RAN vendors have been requesting to have. But obviously, when you have a single physical server, you have a issue of high availability, how to handle that, and at this point, that is left to the responsibility of the workload or the application vendor, RAN vendor. But it's a footprinting topic. And the last one, the lower part of the left-hand side is, we call it the remote worker node, where the control plane or control part of the OpenShift cluster is in regional data center and with high-speed connection to the edge, where the single server is only having the worker nodes, nothing on supervising or management or anything like this. And then on the right-hand side is the multi-cluster or advanced cluster manager, which is managing all these clusters in the network in geographically distributed way. A few very, again, high-level description of the models, RAN models on the left-hand side, which is one of the reasons why 3GPP did this disaggregation model or functional split model to give flexibility to build cell sites based on the environment, also connectivity and other other characteristics in the environment. So again, the first one is, or the distributed RAN, as I call it. Everything is still on the cell side, radio unit, distributed unit, and centralized unit. It looks like a traditional RAN, but it still has the three entity model and interfaces between those. And then you can start centralizing the centralized unit first and have mid-haul between DU and CU. And then if you have a fiber connectivity to the cell site, then you can centralize also DU to the edge site or some similar place and kind of simplify the cell site. And again, the cloud platform, the same cloud platform can and should be deployed in all of these places to make end-to-end management and end-to-end automation easier to implement for the network. Now, this is a bit complex slide, having the nitty-gritty latency numbers between these tiers, and there's not much what we as Red Hat need to kind of control, or we don't control anything, but we need to understand all these latency numbers, even on the transport layer at the bottom, and then different use cases on the top, like IoT and enhanced mobile broadband and all these things, because when you look at the end-to-end communication on these slices, there is a certain latency budget allocated to the cloud platform as well. And we have to understand exactly what is the latency budget we can use in all of these different tiers. That's why I try to keep this diagram as accurate as possible. It's kind of hard sometimes, but we just need to understand what is the latency budget allocated for us. Now, quickly, the three features I described earlier. So the real-time feature. So we have a model that we can partition the multi-core CPU on the right-hand side into, we call it housekeeping cores, where you can run pretty much any workload, and the real-time cores where you can run the real-time workloads only. So, and the partitioning can be done dynamically. So the more you need the real-time cores, the more system gives the real-time cores and vice versa. And with this model, we can achieve the requested or required scheduling latency numbers. Then the synchronization thing, this is a map of the country, and this plotting is a real plotting of one of the US operators, and there's about 500,000 cell sectors, and everything needs to be synchronized down to 1.5 microsecond timing error or accuracy, just to quickly show the challenge here. And now coming to O-RAN Alliance timing profiles or configurations, they have defined few things. And if I start on the right-hand side, the yellow box, that's the reason why we need to be, we need to worry about that, and we need to develop this. So O-RAN Alliance had made a decision that timing and synchronization in cloud-based radio access network is responsibility of the cloud platform. And there's a clear logic on that, because the idea is that that eventually, when things get more mature, there can be multiple DU workloads on the same cloud platform. So the DU workload cannot control the timing, because there would be many guys trying to control the same thing. So the timing control and timing distribution is on responsibility of the cloud platform, and that's why we need to do that. And we are doing that. We have been implementing not all, but most of these things already. Yeah, all these 4 different O-RAN Alliance specified timing profiles. Just a quick example of one of those, which is the timing profile C1 and C2, which are very close to the same. So this red thing is that's a distributed unit, and then we get the grandmaster clock from the satellite into the NIC card, which has the GNS receiver, and from that the Red Hat, the precision time protocol software in the Linux kernel, is distributing the timing information towards right-hand side, which is a DU workload from the RAN vendor, whoever the RAN vendor might be, and also to the left-hand side, which is over the open front haul to the radio units. And there is a really strict accuracy requirements how to do that. So just as an example how to do it. And then an example, which I'm not going to go through, is how this whole thing is implemented in Linux kernel, RHEL in our case, or RHEL Core OS in our case. But just pointing out one more time that it's all done in Linux kernel communities out there, upstream communities. So everything we have done for the Linux BTP is also available to any of our competitors and partners and customers. It's an open source code, and we don't own it. It's our common stuff within the whole industry. Our normal model, nothing special. And as I said, we are kind of studying the Sync-E right now and developing a Sync-E, although we are not quite sure if Sync-E is even needed. Not sure. We might need it, we might not need it. And we are making doing a lot of measurements on Sync-E to figure out if we need it or not. BTP is there, precision time protocol is there, and works well. Then the accelerators, hardware accelerators, and this is an example of what we have. Intel FPGA N3000, which is the most commonly used at this point. A bit expensive, but works well. And the Intel eASIC is the next one, and then we're working with NVIDIA's and everybody else to have other accelerators, depending on what our RAN workload vendor partners need and require. So we integrate what they need. And we have the concept called operator, not network operator, but Kubernetes operator, which is that a configuration and maintenance and management model a little bit outside of the Kubernetes platform itself, where you configure manage different things. And we have developed this thing called OpenShift Performance Add-on Operator, which is configuring all these very low-level important things like enhanced platform features and CPU pinning and SRIOV and real-time kernel, and also the timing and synchronization. Very important thing to have. There are many other operators as well, but this is just as an example. Now, quickly, OpenShift is based on Kubernetes, hosted by Red Hat Enterprise Linux or Red Hat Enterprise Linux Core OS, optimized for running containers. Kubernetes is the core of the whole thing. Then we have a lot of additional features, platform services, application services, developer productivity, whatever you have. And then on top of that, even multi-cluster management, cluster security based on StackRock's acquisition 1.5 years ago. And then Quay, a global registry for containers that has to be somewhere. So it's a very rich platform to have all these things as a development platform, but also as a runtime platform. Now, when we deploy OpenShift on the edge, radio edge, or any other edge use cases, it's not this whole thing. It looks like this. So on the right-hand side is the hub cluster, which I just explained, the full OpenShift. But on the edge, we deploy only the necessary parts of the whole OpenShift. It's still a Kubernetes cluster, but because of the performance and footprint requirements, we just deploy whatever the minimum amount of or minimum part of the Kubernetes, so that we can deploy the edge applications, DU, CU, and other edge applications, just to make a point that we don't deploy everything. Now, quickly going to the summary part. So just quickly showing the Open RAN ecosystem. So we, of course, have system integrators, OEM hardware partners, service assurance partners, and obviously, importantly, the RAN vendors. Pretty much most of the RAN vendors in the world are listed on the upper left-hand side on this slide. We work with all of these, and eventually we'll have productized version of disaggregated RAN with all these guys. Then one more thing is that we finally have a big lab built in Massachusetts, end-to-end lab, where we are bringing partners, even radio units in the Faraday shielded room, and disaggregated part of the RAN and core network, OSS, BSS, management, automation, all these tools, different hardware vendors, servers, and silicon and boards. This has been under building from last summer. It has been a little bit slowed down because of the component shortage and all these things, but it's almost done, and we can start demonstrating things on Red Hat open source technologies in this lab. And that's it. I'm probably used a bit more time than I was planning, but that was my 30 minutes. I hope it was useful to some extent, at least. Thanks a lot for listening.
Thank you, Timo. And we do have a few minutes to take questions from the room. No hands raising. Oh.
Kia ora, Timo. How's it going? Thank you for staying up late. This is a plugged question because I work with you. Is there anyone where you can actually tell production deployments at this point? Can you give us some real world where is this going on? Maybe just geographies might be helpful.
So, there are, I don't know, tens of trials and POCs in all geographies, in APAC, in EMEA, in Americas, all of the places. Production deployments are still coming. We believe that this year, maybe even within the next few months, there will be. We will start seeing production deployments on Open RAN. Of course, we all know that there is an Rakuten Mobile in Japan, which is kind of an early phase Open RAN. It is a disaggregated model, started with 4G, Nokia 4G radios, and Altiostar DUCU running on Red Hat OpenStack specifically, not OpenShift. So that has been there, and that has been in production for quite a while already. But other large-scale production deployments, nothing yet. But we know Dish Network, we know Verizon, we know all these things, guys who are building Open RAN-based mobile networks. But the really big, large-scale deployment, that we haven't seen yet. But I think it's only matter of few months that we'll see few, and again in all geographies.
So Amazon is planning on launching a cloud private 5G service. Do you know if that's going to be Red Hat underneath?
I cannot talk about that much.
No other questions in the room? No. Thank you very much.
Pleasure. Thank you. Thank you.
So next we're welcoming Peter Gent to the stage. He's from Radio Spectrum Management, and he's going to give an update on spectrum for broadband. Thank you.
Tēnā koutou no ingarangi aho kia Wellington aho e noho anō. Ko Peter Gent aho tēnā koutou. Good morning, everyone. First of all, thank you to NZNOG to inviting us along and allowing us the opportunity to give an update. I think it's been 4 or 5 years since we've been here, so appreciate the time you give us to engage. Let's see if the magic button works. Need some radio spectrum. Come on. There we go. Right. This morning, going to cover 6 topics, and obviously introductions a 7th. So some of these, what you've heard over the last couple of days will actually be, I won't say familiar, but we'll be covering some of the ground that some of our previous speakers have noted, obviously from a different aspect, being as we are the government. So, there we go. So who are Radio Spectrum Management? We are part of MB, so that's the big ministry. Whoop, nope. Let me go back. There we go. Step away from the button. So MB, so we, for Radio and Spectrum Management, we are the part of MB and part of government that provides advice on regulating spectrum. So that's everything from, we say DC to daylight, but technically it's 9 kilohertz to 300 gigahertz, I think is what we're legislation mandates to look after. We run 3 teams, so we have an investigations team. So those of you out in the operational areas may have met our investigations team over the years. They're based Auckland, Palmerston, Auckland, Hamilton, Wellington, Christchurch, and Dunedin. We've got a licensing team who run the big register of radio frequencies, which we'll talk about later in terms of the upgrade. And I'm part of the policy and planning team. One half of our function is to provide advice to the Minister of Digital Economy and Communications. And I think some of my colleagues are in the room from parts of my branch. And my side of the team looks at forward spectrum planning. That includes our international aspects. New Zealand, as you can well imagine, is a technology taker. We're a market of 4.5 to 5 to 5.5 million consumers. The stat we used to use, unfortunately it's probably a bit out of date now, is Nokia when Nokia actually still made phones themselves, would make 7.5 million handsets a day. So you can imagine where New Zealand sits in the ecosystem and sales pitch for handset development. So, yep. And we operate under the Radio Communications Act 1989. There are some associated radio regulations. It's quite a, I'd say, quite a dull piece of legislation, but it is what it is. And yep, you can go and read it if you want to read it. Right. What's the next one? Right, so first up in terms of topic, we're going to talk about next generation mobile. So my colleagues and I kind of argued over the title of this section. I went for 5G, he went for next generation mobile. So we'll go with that because in a few years' time, we'll be here talking about 6G and then 7G and then 8G possibly. Anyway, back in 2018, we consulted on where we think we should be heading in terms of spectrum usage for next generation mobile devices. We have been looking at, or we looked at 600, 1400, 3.5 gig and millimeter wave, so that's the 26 to 28 gigs. Those 4 bands have emerged as kind of New Zealand candidates, and different bands have different properties like the physics, and also different amounts of spectrum available. We kind of tend to work on vaguely logarithmic scales. So what we call sub 1 gigahertz, so that's 600 megahertz, typically only has maybe 40 to 60, depending on how the band plans go. Whereas in the millimeter waves, so the 26 to 28 gigs, there's potentially up to 4 gigahertz of spectrum or thereabouts. So, yep. And the typical physics is the higher the frequency, the less distance you'll cover, and the less capacity, well, more capacity, but less distance you'll cover. So it's kind of a inverse proportion. Eric, I think, showed a variation of this slide yesterday. This is the one we roll out. This is developed from the ITU, which is the big UN body that deals with ICTs at the kind of global scale. Enhanced mobile broadband is what, you know, these things are, you know, cellular devices, but 5G is more than that. We have massive machine type communication, so that's our IoT devices, kind of industry stuff. And then we have the ultra reliable and low latency communications. This is the use case triangle. And there are various applications that are envisaged, in use now, and being developed on. And so you can see some of those kind of bits. And obviously, each of those uses have a slightly different, I guess, demands in their properties. But I think for at least most people on the street, this is the enhanced mobile broadband, but it is just one kind of part of the triangle. To delve into the detail a bit more, these 2 diagrams, which I nicknamed Spider, but these are radar, which seems appropriate. So on your left-hand side, you've got various properties. The inner light green is where 4G kind of hit, and the kind of darker green is the 5G areas of their ambitions of where the technology is aimed to be taken over the next few years. And on the right-hand side, you've got the kind of 3 points of the triangle on the previous slide. So the enhanced mobile broadband, so that's smartphones, they kind of hit quite a use case, but then the ultra-low latency and the IoT kind of devices as well also tie into that second diagram. So where are we at? The kind of key piece of work that my team are working on at the moment is the 3.5 gigahertz band. That's been in process in various guises over the last 3 years. We have been doing that pre-pandemic, but the pandemic went and changed some of our work internally. I was talking to 2 Degrees gentleman at the back, noting how work had gone on, and we've got enabled what we call short-term access rights for Spark and 2 Degrees and DenseAir. Vodafone already had rights in the same band. However, all those rights expire in October this year, and so we're frantically working away to make sure that long-term rights are in place, and that my minister is kept very happy as much as possible, and also try and enable our operators, both national and non-national, to be able to access spectrum as they need. In terms of other bands, I won't talk about the 600 here, but so the millimeter wave is something else we consulted on last year in terms of future 5G or next generation stuff. The submissions are actually on our website, so you can go away and read them. The themes that kind of came out were strong interest in the lower, called 26 gig band, which actually starts at about 24.25 from memory gigahertz, up to around 27.5. There's kind of mostly interest from the mobile side. And then the 28 gigahertz band, which kind of overlaps, so starts around 26.5, I think, confusingly, and then goes up to about 28.5 to 30. There's more interest as well from the space sector. So we have some competing challenges in terms of those users. We're still considering those next steps, but the 3.5 gig is our current kind of higher priority work, but we are dealing with requests for the millimeter wave. If you feel like you want to come and access some short-term millimeter wave, come and have a chat. We've already enabled a few of those access requests from some of our, I guess, current Spectrum users. So, yep, short-term use is good. Long-term use, we're not there just yet. Actually, doing okay for time. Might get you to morning tea early, so make me. So I know. Okay. Next up is the MSP, or the Managed Spectrum Park. So the Managed Spectrum Park is a small slice of spectrum at 2.5 gigs, which my colleagues set up, and I have to remember the dates, I think around 2008, and I hope I've got that right. It was designed to encourage flexible and cooperation between users and a kind of self-managed approach. So we set some rules up, and we've tried to let users go and kind of play in the park. The idea was almost like there's a bit of a gatekeeping function, but people go and do their thing. It has worked for most parties. However, the allocation process and the technical parameters of the licensing regime have encountered some problems. And over the last 10 years, disputes have taken a considerable amount of our time and effort to resolve. We did undertake a review last year looking at the operation of the MSP, focusing on the problem areas, including the how cooperation occurs, technical licensing parameters, and potential modification of licenses. So that's why we've undertaken the review. Access is still pending. I know there are people in this room who would like to get access to the band, but the other kind of subtlety on the MSP is that the band itself, the management right, which is the overall spectrum authorization, actually expires in 2028. And our internal processes are to start a review of any expiring management right 6 years out, so kind of start looking at what that looks like beyond 2028. So we potentially will be caught in a bit of a broader piece of work for that spectrum, which is not just the MSP, but there are some national rights held by some of the cellular operators surrounding it. So there's a bit of a quirk on timing, and we're yet to resolve that quirk on timing. Next up, Wi-Fi 6E. If those of you who have been reading developments overseas, Wi-Fi 6E is kind of currently exploding in the equipment market. Lots of other administrations or jurisdictions are doing Wi-Fi 6E right now. It's I can use the pun, a broad range of spectrum between 5925 and 7125 megahertz. Most of Europe and I think possibly the US have a slightly smaller range by a few megahertz, but that's the broad 5900-ish to 7125. The US, for instance, has gone for that whole 1200 megahertz or just about for Wi-Fi 6E, whereas some other countries have gone for a part of it. We undertook a piece of work last year to look at the lower 400 megahertz. I think it's 500 megahertz, so 5925 to 6425. We've consulted on that late last year. Australia has recently made that block of spectrum, so the lower part, available for use for Wi-Fi 6E, and our decision is coming out very shortly if my colleague manages to get the things signed out internally. Bearing in mind, as I said at the beginning, we're a technology taker. Yep, you can read what you want from that. So But yeah, we probably won't be doing too much different from some of our major trading partners, put it that way. Right, new RRF. So hopefully those of you who regularly use our RRF are aware of this. This is the Register of Radio Frequencies. Over the past 2 or 3 months, we have been running demo sessions of our new online registry system. Back in 2005, we kind of went fully online. Almost every license and right that we have is in the public domain. There are a few suppressed licenses. You probably don't need to know about those if you don't use them, or you're a radio engineer. Basically, the underlying software and web stuff is very, very oldie school and is coming to end of life pretty quickly. So we are frantically developing a new kind of back end. The front end, I think, will get refreshed a little bit, but you know, government being government, you only have a certain amount of colors and a certain amount of buttons. So, yep, we are trying to add some features that will drag us into the mid-2000s, such as mapping. We already have APIs available through the big MB corporate kind of data portal, and they will continue as far as I'm aware. And we're also trying to fix things like the back button, which probably everyone in this room will groan inwardly when I say the back button doesn't work properly. But that's one of our biggest bugbears and biggest issues for external users. And personally, it's one of my biggest issues as an internal user as well. So they're going to fix it. It is working. It's scheduled to go live later on this year. If you are not on the mailing list and have not been invited to the demo sessions and you would like to, please probably come and talk to me afterwards, or go on to the RSM website and kind of drop us a line. We're obviously trying to work with our kind of key stakeholders, and we've been engaging those for at least 3 to 4 months. We've actually had a user group going for the last couple of years, just in the initial development stages as well. But yes, if you are interested in seeing that, we're keen to kind of get you on board and get you engaged. Obviously, go live is kind of, there are bits of spectrum which are worth hundreds of millions of dollars in this, so we want to make it go smoothly when it finally goes live properly. But we're keen to take feedback on from users in the technology community. Now, this slide is the slightly awkward slide because I wrote this slide for when NZNOG was going to be in February, and it was going to be, come give us feedback. The consultation's still open. We want to listen. I realized last week, reviewing my slides, that it was no longer February, and the consultation was no longer open. So kind of apologies for not being able to take your submissions, but we encourage you to go and read the submissions. I think we've had 36. They're publicly posted, and we've got one of our best people are on it right now. That's not me, who is reviewing the submissions, and we will be hopefully finalising it with the Minister and publishing that. That kind of tries to, it's our think piece / looking at what we think is going to happen over the next 5 years. Some of our, I guess, other administrations we look to do this on an annual basis. We don't have that capacity to do this every year, but we try and do this as a snapshot. Hopefully, if you want to read a bit more about what we think about and where we think things are going, this is the document at least to kind of start that process. Welcome you to go and read the draft, and hopefully shortly we will have a kind of final 5-year outlook that will kind of be on our virtual desks for the next few years. I'll just check the time, and my phone is now locked. I think I'm still good. 10 minutes, okay, it should be done in under 10, unless questions take a while. So finally is Māori Spectrum's Māori interest in radio spectrum. This was probably relatively low-key to most people in this room, but back in February, the ministers of, and I'll get this, hopefully it's right, ministers of Māori Development, Digital Economy, and I think Finance, and the Beehive website will correct me if I've got those 3 ministers wrong, signed a memorandum of understanding with the Māori Spectrum Working Group to hopefully provide a long-term kind of agreement on spectrum for Māori. You'll read some of the media commentary that it does not negate. There are Treaty of Waitangi processes. It doesn't negate and resolve those Treaty of Waitangi processes or situation per se, but aims to provide a long-term relationship between the Māori Spectrum Working Group and the Crown. So there's some some new stuff, which will change the way we work, at least in some of our commercial bands. So that's typically bands that we set aside for the high value uses such as cellular, and also some funding, some policy, and there will be a new entity that is being proposed that will be set up in legislation over the coming months. There are, for those of you who may be aware of the history of 2 Degrees and even the Māori television service, there are a number of Māori entities which hold spectrum rights already, but this will be a new entity going forward. I'm not aware, and if I was aware, I couldn't comment on the status of those other entities in Māori spectrum, but there is the MSWG. That's kind of in the public domain. If you want to go and engage with the MSWG, that's your prerogative to go and do that. Obviously, I wear the government hat, so we can talk a little bit about that, but I probably can't talk too much more. But yeah, details on the Beehive website, and I think there are some media commentary around that as well. So, yeah. And I think I am done. That means that, barring questions, morning tea is the other side of it, and I'll open to questions as much as possible.
It seems no questions at all. So, thank you very much.
Thank you.
So that brings us to the end of our first session for the day. For everyone in the room, we'll be resuming at 11 o'clock. For anyone watching the stream, we won't be resuming until 11:30 because our first talk of the next session is confidential. So go get yourself some coffee, food and all that, and we'll see you again in half an hour. Thank you.
Check 1 2 1 2 1 2.
We're up. Okay. Right. So our next speaker, we're going back to the government. We've got Ben Oakley from the Commerce Commission to talk about their testing program.
It's always good to follow. Is that microphone working? Always good to follow somebody who's got a hilarious presentation right before you, isn't it? Thanks to Simon for that. Kia ora, everybody. I'm Ben Oakley. I'm from the Commerce Commission. I'm a manager in our telecommunications regulation team. Thanks to Richard and NZNOG for having me here to talk to you about our broadband testing program. Big green button. That's the one. Awesome. Thank you. So what I'm going to cover today briefly, the boring stuff, the Commission's role in telecommunications, and then a bit of a history and purpose of our NBNZ program, what the program does, and then what the future of that program hopefully looks like over the next 3 to 5 years. So I'll cover this pretty briefly. Our role at the Commission in terms of telecommunications is to regulate the price and quality of certain broadband and phone services, and then monitor the competition, performance, and development of the industry as a whole, and provide that information for those that are interested. Our traditional role has been to kind of focus more on the wholesale side of things, so predominantly the price and quality of Chorus's copper network, and making sure that you can do things like take your mobile number when you switch providers. But we had a review of our legislation, the Telecommunications Act in 2018, which has slightly changed our focus in a couple of ways. So we were required to set up a new fiber regime, which is now in place to regulate fiber. And we've also received new powers to monitor and improve retail service quality, which is things like customer service, billing, speed and performance of your services, and provide that information in a way that helps consumers choose the right services for their household. And that's where our testing regime comes in. So I also have a bit that the lawyers make me say when I do these kind of presentations, which is why we're here. So we aren't here to promote any particular technology. We think that all technologies out there have got a place to play for different consumers, be that based on speed, plug and play installation, or economical choices for rural customers. But these events are really good for us to be able to raise awareness of what we do. This particular program makes up a decent portion of how we spend our funding. So it's really important for us to be transparent in how we spend that, what the testing does, and what we hope to get out of it. As will become quickly apparent, I'm not a technical person, so I'm happy to take any questions at the end, as long as they're easy ones for me. And we also do have an open tender process as well. So there's a limit to the questions I'm able to answer about that, but I'll explain that more in a second. So we've always tested to some extent since about 2007 broadband performance. We used to have a much smaller program, which was very useful for shining a light on broadband performance and did a good job of showing that performance as New Zealand went through a number of technical developments. But partly in response to the new legislation and the focus on providing information for consumers that's actually useful to them, we set up an enhanced program in 2018 and contracted SAMNOs, who are a sort of a global leader in terms of broadband testing. They work with a lot of regulators around the world to test the kind of things that we now test. And the way that our program works at the moment is it's a volunteer-based scheme. So we have 3,000 little white boxes or probes that you plug in at home as a volunteer into your router, and it performs a series of tests around the clock to simulate broadband usage. That information then gets aggregated up, and we're able to produce regular reports that break down technology differences and, where we can, differences between retailers as well. So at the moment, we test the larger 7 or 8 providers across ADSL, VDSL, fixed wireless over mobile networks, a couple of fiber plans, and one of the plans over HFC as well. And the main aim in the program is, as we've got there, to provide that information to consumers to help them choose the technology and the provider for them. But a secondary purpose, which is actually, we've probably had more of the success in the program so far, is shining a light on that performance hoping that the providers then compete on quality and not just on price. But also what we've seen, as I'll demonstrate in a second, is actually where providers have been willing to engage with the data we're able to publish, we've actually been able to improve certain plans on the networks as well. So I've pinched a couple of slides here directly from SAMNO's, which I won't go into in a massive amount of detail, but basically just demonstrates that in terms of what we actually test with the white boxes that are out there, there's the standard kind of quality of service test, which I'm sure many of you will be familiar with, your upload, download speeds, latency, packet loss, jitter, and the like. But what we think is perhaps more important for your average consumer on the street is the quality of experience testing that it does that we're able to report on. So latency to overseas gaming servers, the comparative performance of different social media and video conferencing platforms. That one in itself has shown quite an interesting difference between the free video conferencing platforms and the paid for platforms. And then video streaming testing as well as another important one. So we test to Netflix and YouTube servers within the providers' networks, as opposed to the quality of service testing, which relies on our kind of neutral servers around the country. And as I mentioned before, one of the biggest successes we've had from the program so far is this case study here, where a few years back, we identified that the Fiber Max plan, which is effectively the wholesale gigabit plans, showed quite a degree of variability that we weren't expecting, and certainly wasn't being observed in other countries where SAMNO's tested these plans. And it was sort of topping out at an average of sort of 500 to 600 megabits, where it should, in theory, be north of 850. And as you can see there, that you probably can't read the chart, but the dark blue bars are the sort of the pre-investigation bars, where ranging from speeds of 450 to 900. And so because we've taken the opportunity to try and be a bit more transparent with this program and provide all the raw data, we were able to work directly with SAMNO's retailers and wholesalers to look into this particular issue, and a few things were identified that led to some changes across the network. So we added an extra server in Christchurch to try and improve things in terms of routing destinations. Retailers made some network changes on their side, and wholesalers, in particular Chorus, made some changes to their network. Things like some of their older generation ONTs were improved, and that resulted in the green bars, which is a sort of a 35% increase in speed and a massive reduction in variability on that those gigabit plans. So quite a big win, we felt, for consumers, and probably one that we weren't quite expecting, given the main purpose of this was to provide information to consumers, that the sort of being transparent and being able to work with the industry players has been quite useful for us. This is just taken from one of our recent publications. So this is more what the consumer would see from our quarterly reports. This is just an example of download speeds, so presented across the different technologies. We've got 24/7 download speeds in the light blue bars, and then peak hour speeds in the dark blue bars. And what we've been quite pleased about is over the lifetime of this program, we've been able to look at the data at times where we expect usage over the networks to be higher, like the Rugby World Cup, like the lockdowns that we've had through COVID. And we've seen actually not too much drop off in terms of that increased usage, as we also do in peak hours. We don't see too much of a drop off across the networks, which has been really good. As a volunteer, a green button works. As a volunteer with a white box plugged in, you also get some extra benefits as well. So this is just an example of a dashboard that you get across sort of 3 or 4 relatively easy to understand metrics. We've seen this used in diagnostic conversations with customers and their retailers, which has been really useful. Also seen examples where this has actually been taken to the telecommunications dispute resolution scheme as evidence for, hey, it's not my home network or my Wi-Fi that's the problem, which is usually what my retailer is telling me, but actually the speed and the connection into my router, which is provided by the RSP. So as a volunteer, you get some benefits of being part of the program as well. But there's definitely some limitations to the program. So we extended our 3-year contract with SAMNO's in June to roll it over into basically finish this September this year. And then we did a review earlier this year into the success and the limitations of the program. And while we're pretty happy with what we've been able to produce, and it's been a step up from what we had previously, there are a number of limitations which we're now looking to try and improve over the next 3 to 5 years of the program. So we're not able, despite having a pretty high proportion of volunteers to population, actually one of the highest in terms of people who regulators that work with SAMNOs, we've still been unable to get enough volunteers to sort of break results down geographically to the level that we'd like. Even though we only test the larger providers at this point, there are a number of plans that we haven't been able to break down by retailers because we haven't been able to get enough data for the results to be robust. And so that's something that we'd like to be able to improve in the next version of the program. We also, the boxes that we use don't test or can't test above 1 gig, which has meant that we haven't been able to test any hyperfiber products yet. And that is somewhere we assume consumers will start moving to, and something that we'd also like to test in the new version of the program. And we also, as I've said earlier, only test the largest 7 or 8 providers currently. And we know a number of smaller providers that would like to be tested and reported on. And that's something that we'll be looking at as we contract the next program. We also asked consumers what they think. And on the left-hand side, as you look at it, a great result is 97% of people think that it's important that there is independent testing of these kind of metrics. The less good chart on the right is that 83% have never seen any of our reports, despite publishing them every quarter for the last 3 years. So that's something that we're going to have to work on as well, thinking differently about how we get these results out and put them in the hands of people to be able to choose the right technologies and providers for their household. So in terms of the future of the program, we've got an RFP open at the moment, actually closes, I think, 11 PM on Monday night for anyone out there that's still interested in bidding. It'll be a 3-year contract with the ability for us to extend that for another 2 years. It will hopefully have a larger sample size. The minimum testing requirements are what we've got already, but ideally we can go further with more sample. We'd like to be able to test hyperfiber and satellite, smaller providers that we don't currently test. And we also need to consider how we maybe incorporate private data into our program as well. So something that we're seeing overseas and starting to happen a little bit more in New Zealand is retailers embedding testing into their routers that they provide to consumers, which allows for a much greater sample size. And we'll need to consider how we could perhaps bring that into our reports as well, so that we can report on as much as possible. And that's pretty much a whistle-stop tour of what we test, why we test it, and hopefully what we're going to be able to do in a new version of the program coming soon. Any easy questions?
Thanks, Ben. Out of pure curiosity, do you know roughly the figure of how many white box or SAMNOs white boxes are actually out there in the field?
It's north of 2,500. So we have 3,000 that we basically bought over the lifetime of the contract. About 2.5, I think it's more than 2,500 have gone out. There's then a difference in there's a series of drop-offs. So once you ship them out, because they come from the UK, a lot of people, there's a surprising drop-off from people who have signed up to then people who don't ever plug it in, or people that plug it in, see that their internet's actually really good, and then have less reason to keep it plugged in. And that's been something that, I mean, it's kind of an altruistic reason to keep it plugged in once you've worked out that your connection's fine, right? And we see people only plug it in when they then have a reason to plug it in to check their performance again and get that diagnostic information. So yeah, that's something that we are thinking about for the next version of the program, is how can we incentivize people to sign up and to keep these things plugged in, because the information is really useful for perhaps not just yourself, but for other people.
So this, hi, kia ora. So I had one of these. I was one of the first people to sign up for it.
Sure.
The box is a piece of shit. I mean,
good. I'll pass on.
And that's why I dropped off, because it
Right.
was slowing down my internet. Right, like
Sure.
literally, if in the most appropriate way to put it in is you put it in line between your WAN turnover, right, between your network. That was literally causing my network to slow down between 200 or 300 megasecond, because the MIPS processor in this box can't handle, and that's on a standard gig uplink, right? And now I've got hyperfiber, it's junk. So yeah, there's the appliance route I get is the easiest way of doing this. There's got to be an agent way of doing it. Like if I could download a container and chuck that on a server that's actually running my network, then I'd be much happier to continue running the probe.
Sure. Thank you for the feedback. You're not the first person that's mentioned that to me, and we have passed that sort of thing on to SAMNOs. They do quite a lot of testing around the clock to try and give the people who contract with them the best boxes that they can. And there are more advanced boxes out there now that weren't there when we started this regime. And SAMNOs, I imagine, will bid on the next version of this contract, as will others, and we'll look at the different options of testing. As I mentioned, with more providers moving to embedding testing into their routers anyway, that could be a way that we could. I think that's where we will likely get to in the future. Maybe not for this next version of the program, but something that would hopefully sort of alleviate any concerns with the performance of the internet itself, but also help us get around some of those sampling issues that we've got as well. In terms of volunteer sign up, you can imagine if everyone's got it in their router anyway, obviously comes with a bunch of privacy challenges that you've got with that, but would allow us to hopefully represent the data on a much more granular basis for consumers to be able to choose, like literally what's the performance like at a property I'm going to go and buy, kind of thing. This is more questions than anybody else had. It seems unfair.
Hi, are you considering moving the independent test servers off RANs and maybe behind public IXs?
Possibly. That'll be something that we have to consider. So the arrangement that we've got at the moment was largely because of SAMNO's arrangement with MLabs, which led to us sort of choosing those RAN servers in particular locations. That's all up for grabs in the next version of the program as we look through what the proposals are.
I've got a question. In terms of consumer engagement with the results, is that something that Commerce Commission is taking on, or is that something you're going to push to your test provider, or?
Likely to be a bit of both. So probably something that we didn't give as much consideration as we could have done in the current version of the program. It was obviously a step up from our previous program in terms of, and we've got that data to show that how many people view it. But you can obviously see from that chart that I had up before that 83% of people have never seen one of the reports. So one natural way now that we do think people will engage with these results is that a code that the TCF's just published based off some guidelines that we released last year is now requiring the use of this kind of information in RSP advertising. So I'll move away from up to speeds and more to kind of expected peak time averages. And that's a kind of a secondary way that we think people will engage with the results, which is great. But we will need to think about how do we promote it a little bit more. We have been on the likes of 7 Sharp and the AM show, but more from a kind of getting us volunteers kind of recruitment basis. And I think we can hopefully move to more of a how do we represent this data in a way that people can use it and find it.
Okay, I think we'll thank Ben. It's nice when the government is here to help.
Yeah, thanks.
So it's also nice when you're running ahead of time. So our last presenter for this section is Beck from Cisco. And Beck's here to talk about network testing.
I think it's still good morning, right? Good morning, everyone. My name is Beck. I'm a system engineer working for Cisco New Zealand. I'm here to talk about network testing, more on the open source side with Cremon KVM. So I want to start with a why and why not. The why side is mainly because hardware are great, real boxes are great, but you don't always get them and you may not get enough of them. And also it's actually difficult to set up or time consuming, costs a lot of money, all sorts of reasons. And also vendors has actually made a lot of progress over the years about building the virtual node images and also making them available to users. What also helped over the years was the move or convergence towards x86 and ARM-based control planes, because it used to be MIPS and the old, well, probably not old, but old RISC instruction set that running within those routers and switches. But converting them to x86 and ARM has actually helped a lot. And then it's actually easier to set up and automate, as you could imagine. And furthermore, is that you don't really need to have a pure virtualized test setup. You can actually do a hybrid. In fact, I'll actually show a sort of example that we used in one of the delivery projects before, which is actually a hybrid setup. Onto why QEMU and KVM. It's cheap because it's open source and free of charge. And also it has very wide support. If you go to like vendor documentations on the support of the virtual nodes, mostly you will find QEMU, KVM, VMware, and some other hypervisor technologies, but usually QEMU is there. And I'm not here to actually convince you guys that if you're already using stuff like EVNG, CML, and other GUI-based tools, I'm not here to convince you guys to move towards QEMU. But QEMU is the actual underlying tool being used. So hopefully this can also give you some ideas on how things work actually underneath. You don't need to be a Linux expert to use it as well. Because I do networking. I don't know that much about Linux. So my knowledge mainly has come through fierce Googling and some late night reading to help with sleep. What's it not good for? So generally, it's only good for control plane or layer 3 related functions, but you can actually find out a lot more in your vendor documentation. So reading the documentation is actually very important. It's generally not good for any performance, convergence, or scale related testing, because a lot of the virtual devices would be used internally by vendors for basic testing. They're not really for production. There are virtual nodes for sale, but we're here to talk about testing. They're also, generally not suitable for hardware dependent features. Cause is very notable. Also, some virtual devices does not work well with layer 2 based technologies. Again, you have to read the docs or you have to find out by yourselves. It may not have feature parity with whatever hardware, whatever real hardware you have in the production. So that's also one thing to note. This is an example that we used in a delivery project. So on the left-hand side, you will see those big round circles. Those are the physical part of the lab. The big square is the virtual part. So you don't have to understand the details, but the idea was that we wanted to do performance and scale testing with real devices. We also wanted more nodes to be able to do validations on segment routing and a bunch of other features. So we need to know whether the behavior is what we are expecting. That's why we put in a lot more nodes. And you will notice that we actually have a ESXi host, and in it we actually ran a Linux host. You don't really need the ESXi. It's just how things were set up when we were given the lab. One other thing I've not mentioned here is that virtual nodes can be very helpful if you are working on development on your automation tools or strategy, because you can easily spin up a bunch of copies of the test nodes, and you're not necessarily testing whether the CLIs that you put in is actually functional. That should be validated with real hardware. What you really care about normally is just whether the CLI is accepted and the interaction between whatever your automation tool you're using and the actual device. Cool. I'm going to go through mainly 4 sections, some basics on virtualization, building a single node, and how do you bring up a topology. And then just touch upon initial configuration. Are we all quite familiar with the basic concept of virtualization? Because it's been out there for some time. So I'll go quickly on the basics part. So your routers and switches pretty much a PC. If you take away those forwarding magic, that was not an earthquake, right? So what you really need is a image or network operating system coming from your vendor. So you need to talk to your vendor to get those, and a host to run the software. Right. On the host, pretty much any processor released in the past decade would work. You can do with Intel and or AMD, but in terms of official support, Intel is generally much better because a lot of the vendors has been using Intel as the actual control plane for their real devices. I actually wanted to do some validation on AMD platform when building this deck, but unfortunately my AMD host died. So sorry about that. I couldn't give you guys more information, but from what I heard, CSR1KV may have some issue working on AMD platforms. I was able to bring it up and do some basic CLIs, but I just didn't get a chance to do further validation. RAM, yeah, so it depends on what node you plan to run. I'm just giving a few examples, but check this in the documentation. So both processor and RAM, you can actually overcommit. So you don't have to say, I have a 16 gigabyte RAM, then I can only run 2 instances of XIV9K, and that's not necessarily the case. And quite often, after some time, so after the boot process, if you give the node some time, the RAM consumption usually comes down. Processor is actually easy to oversubscribe as well. And we're talking about testing, we're not talking about production. So disks, again, varies from node to node. What's important to know is some of the virtual nodes, the disk space will expand after the initial boot. So you'll need to test that out, make sure that you have enough space available. Yeah, again, read your vendor docs. Software, I'm sure you guys can find plenty examples online. Most important, most commonly used 2 binaries are the Qimo-System-x86-64 and the Qimo-RMG, because you may need to work with the image file. Okay, so node images, what you typically get would be either VMDK or an OVA. So if you get an OVA, you can just extract it and convert the VMDK to QCOW2. In the case if you get an ISO file, you may need to, well, you will need to create a blank QCOW2 disk and perform, boot it up and perform the actual installation. Another note on the image file, typically, I mean, almost always, you will find the requirement of 1 image file per node. So you can either make multiple copies, or you can use what they call QCOW2 backing file, which is, I think it's a similar concept as a snapshot. So I've included a couple of links on the backing files. it can help save you some disk space. Bringing up and building a node, actually you need to spend some time reading the vendor docs, because there's tons of options available in Qimo, and vendor documentation will let you know which options are needed and how you may use them. So one thing I've noticed is some of the vendor docs are actually quite old, and because Qimo is an active project, so sometimes you will find certain options got obsolete or just simply got removed. In that case, you'll probably just need to go through the Qimo docs to find out what's the new option. And if it's deprecated, you'll get an error message, but you can still use the option. I just need to find out what's new to use. If the argument is removed, your instance wouldn't start. This is just an example. I think I'll use the laser pointer here. Apologies, people over there. So I'll just quickly go through some of the key options, right? You want to give your node a memorable name, hopefully a good naming convention. This is the RAM side. So you set up how much RAM in terms of megabyte that you use. This is how many cores you want this node to have. And this is obviously your image file. Note that depends on the node that you're running, this may look different. The serial option is usually your console. So that's the first thing you can actually access. You can actually access even before the node is completely up. And we typically do it through telnet. So once the CLI is accepted by our Linux host, what you do is just telnet to the port, and you will get the console. And then the rest of it is adding interfaces. I'll talk a little bit more about them later. All right, this is just an example. You'll see they look pretty much like your real devices, except they're not. This is another example with 3 interfaces I've added to, to an XRV node and a CSR 1kV node. You will notice that the interface is actually mapped differently. So again, this is what you need to find out with the vendor documentation. In the case with XRV, the first interface is mapped to a management. So this is actually out of band. You can't carry traffic. In CSR 1kV, it's a bit different. These are the examples that you may find in documents. Some of them are like this, a wall of text. The others may be a bit more helpful with a graphical representation. So we'll see XRV first interface mapped to management, then second interface would be your first traffic carrying interface. XRV 9K is different again, where your first 3 interfaces, well, actually, your first one is mapped to the management that you can use. Second and third is actually reserved for internal use. You can't really use them. Your so-called production interface standing with the 4th NIC that you add. And once you're done with the testing, depends on the node that you work with. With Cisco nodes, you typically just kill them. Right? You don't need to worry about anything, but read the docs. Some of them may need you to gracefully shut them down before you kill the process. What you'll not also notice is that, this is actually one line of command. And within this command, we're actually putting a bunch of interfaces. You can't really add more with Qimo CLI. You can't add more without actually killing the node. So make sure that you have plenty of the interfaces before you bring this node up. Cool. Making connections. So once your node is up and running, you want to connect them. there are actually many ways how you can connect them, but I would say the easiest, coming from a network engineer point of view, would be bridge, because the Linux bridge is pretty much just a switch or a VLAN of a switch. So what we typically do is you create some interfaces, you just add them to connect them to a bridge. So this interface option actually has two lines or two arguments. One is the device part. Now the device part, you actually need to be quite careful, because that's this is the so-called the driver appears within the virtual node, right? So that's your VNIC if you're coming from a VMware world. It needs to be supported by the vendor image. It varies from image to image as well. The other part is the NetDev part. This is where we use a tap interface to connect to a bridge on the host to make a link. I'll show you more examples. And what's important here is that the NetDev option, the value of the NetDev option or the device argument needs to match with the ID of this NetDev argument. As long as you match them, then that's fine. And they need to be unique. So if you want to add 10 interfaces, you can start from 0 and then end with 9. That'd be easier to manage. After the node bring up, what you will see is a bunch of tap interfaces. The reason why you see them as tap interfaces is because I named them as tap interfaces. So whatever your name here will show up in your if config or IP link show. This is a graphical representation of how things look like. So when we're making a connectivity between two nodes, what we do is here is we have a tap interface, which is mapped to a interface in the virtual node. We have another pair of those guys. What we do is just create a bridge, and then you add these two tap interfaces to the bridge. And that will make a link. What we can't do here is convergence testing, because if you kill a bridge, the tap interface is still on. So yeah, no, the interface in the router doesn't go down. Because it's a bridge, what I didn't mention previously, right? Bridge is basically a switch, so it does destination MAC forwarding. A lot of the devices, if you don't specify MAC address, they use a very simplistic rule to come up with a MAC address for each of the interfaces. And that might cause some trouble when you want to, like, say if I have a matching or I have the same MAC address of two devices connected to the same bridge, obviously forwarding doesn't work. So you want to have a little script just to randomize your MAC address. Right. This is more about management, because you don't want always access through the console. You want SSH. So what I'm doing here is just one example. So one of the ways you can do it is, because I started all this with a home host. It's just a PC. So there's only one interface. So you can build a bridge. What you can do is you add the actual interface, the physical port of your host to this bridge. You give this bridge a IP address. So sort of like an SVI if you're coming from the switching world. So that's for management of your host. And whatever the first interface that you have on your virtual node can also be connected to this bridge. So you can assign IP addresses to them and reach them directly through your home network, your lab network. Right, so that's pretty much about it. All you need to do is just have a CLI to bring up the node, create the connectivities, and you will have a topology, right? You can actually put them into a single script if you want. I actually have a example here. The slide deck will be published, and these part are actually text, not screenshots, so you can actually reuse. So I'll start from the lower part, because what you do is you just want to have loops to create multiple instances of nodes and probably multiple instances of your interfaces. So you can have a section dedicated for your nodes. You can have another section dedicated for your connectivity. And what I did was I added topology ID because I wanted to be able to run multiple topologies at the same time on a single host. I mean, I'm actually not a programmer, so you just modify the script or come up with your own. Day zero configuration. This should vary from vendor to vendor. Again, all Cisco virtual node comes with a process called CVAC. So basically, if you have a text file, you can make them into an ISO image when you initially booting the node. So when the node does not have any configuration, you can use the text file that in the ISO image as the initial configuration. So it helps with initial setup. Other stuff like POP and TFTP auto configuration, again, depends on your image. So the Nexus 9KV image actually works with POP. So if you have POP infrastructure, you can just use it straight away. Again, read the vendor docs. Last part is test traffic generation. I was going to do a bit more on this, but it's going to be a bit too much. So, I mean, obviously, depends on what you have as the test endpoint. You can have a router, do multiple VRFs for testing, and you only get ping in that case. Or you can have like a Linux host attached that you can run applications, you can run more test software. Or you could run traffic generators, Ostinato, T-Rex, or even real traffic generators. But I would say, yeah, try not to, because a lot of the virtual nodes are actually rate limited. Cool. That's my talk. Questions?
Any questions?
Lunchtime.
So that brings that session to a close. Now it's lunch. We were actually a few minutes early, so I'm not quite sure if the food's out yet or not, but lunch will be ready at 12:30. And we will start again at 1:30 for the next session. So see you then.
Everyone, we're just going to kick off the afternoon session in a few seconds. Okay, hello and welcome back. So hopefully everyone's managed to have a bit of lunch, get a bit of caffeine into you, maybe wake up after last night and all that. So a couple of things to cover off before we introduce our next speaker. There's still a few bags left from the conference, so if you haven't managed to get a bag yet, especially if you're a late registrant where we kind of told you not to get a bag, feel free to pop into the room just over there, grab yourself an NZNOG bag. One thing you'll find when you get your bag is there's a little mystery card. So I'd encourage you over the next hour or two to maybe have a look at this, work out what it means and try and follow a few clues. Then you may even get something at the end of that. Also, like a lot of people have got these really cool hoodies that I'm sort of modeling here. So anyone that's a member of NZIX can come and get one of the NZIX hoodies. But if you're not and you want one of these stunning hoodies, you've also got in your swag bag one of these. You can tear off this little perforated thing here, enter a drawer, and as a non-member, you may win a hoodie, or you might get given a hoodie. That's probably most of my updates. So now I'm going to introduce someone that all of you know. He was absolutely planning to come over here. At one point, he was looking at hiring a canoe to get here. So yeah, Jeff Houston, we've known for many years, one of our favourite speakers. He's beaming in from Canberra, and he's going to be talking about routing security. Hopefully he's around. Yep, there he is.
Hi, and thank you very much. Look, I was all prepared. I had tickets, I had a presentation pack, and someone in my house had COVID. So here I am after a week of sitting in this house going, let me out, and I've been let out yesterday. So I'm coming to you virtually. My apologies, of course. So let me share a screen. And, you know, today, surprise, surprise, I want to talk about routing security. I don't know if any of others in this room has been following the current meeting over in Europe, RIPE. I think it's RIPE 84. But there's this endless parade of RPKI talks. And I'm going to try not to fall into that trap and give you a kind of different view on this and sort of take in some other aspects and see if I can offer you a more balanced perspective. And I'm sure many of you know George Michelson, who also is at APNIC, and I have lent on him for some material used here. All the good jokes are probably his and all the really bad ones are probably mine. And I take full responsibility for that. Let me say at the outset, I'm not going to say terribly nice things about RPKI from time to time, but, you know, don't take it to heart. Don't. I'm not saying that RPKI is so evil you should run 1,000,000 miles. You know, don't believe me if that's the message. You know, that's not what I'm trying to say. But it's not perfect. It's not perfect. Now, there's no plan B here that we can identify. There's only a few tools around, and trying to keep routing together is a really, really hard task. And so by saying it's got some rough edges and it doesn't solve every problem known to mankind, that's true, but it doesn't mean, you know, you still shouldn't use it. It's worth understanding it has its strengths, it has its weaknesses. But I think it's more a message to everyone out there who operates networks for a living and for money. There's a big difference between engineering and fantasy-based bullshit marketing. And sometimes it's necessary to call out what is just wild ass myths coming from the marketing department of your favorite vendor and what's the truth. What actually works? Where is there evidence? What's its strengths? What's its weaknesses? And so I'm trying to give here, I think, an honest appraisal of where this technology is at, what works and what doesn't. Because RPKI and this whole issue of routing security is not magic pixie dust. It doesn't cure everything. So we often quote the great YouTube incident, and I'll get back to that later. But I want to quote something a little bit more different. The Ethereum attack in 2018. And for those who weren't paying attention at the time, I'm sure there were one or two, but not that many where everyone else kind of knew it. It was an interesting attack. It was very rapid. It first started with a routing attack against the DNS. And instead of being able to reach Amazon's Route 53 authoritative DNS servers in Brazil, you were in Brazil, the attack was sort of highlighted there. The routing attack said, no, those addresses are over here. More specific announcements from their own evil DNS server. Now, they could have been careful. Those more specific advertisements could have actually faked Amazon's original AS number. They didn't even bother. They used their own AS number, 102.97. If we were doing a basic ROV protection, that would have found it. But on the other hand, if they'd have known that, they would have just faked the original AS, so it wouldn't have mattered. Because they were faking someone that had a lot more knowledge than they were, for every domain that they didn't know anything about, they did the obvious DNS thing. Don't ask me, ask someone else. Serve fail, which is brilliant. No one else noticed. But if you asked for myetherwallet.com, woohoo, all bets are off, it went to a bad website. Now, your browser said, this is a really bad website. This certificate is crap. Do you want to go there? And a whole bunch of folks said, yes, please. Whoops. From start to finish, couple of hours. Would certificate transparency have helped? From start to finish, a couple of hours. Certificate transparency, not a hope in hell. Anything that took more than a couple of hours wouldn't work. This is quick. This is today's attack surface. Now, interestingly, they got a lot of money and it wasn't even that sophisticated. You should never click through a warning that says, this certificate is complete crap. Do you still want to go there? In fact, I'm amazed browsers still say, are you sure? The answer should be, you're a loony. I'm not going to work for you anymore. I'm crashing. I'm stopping. Go and find a browser that has more credulity than me. I'm not going there. However, they click through. If myetherwallet.com, that handles a lot of money, had bothered DNSSEC signing, you couldn't have given the fake answer. It wouldn't have validated. Duh. Big clue, DNSSEC is your friend, not your enemy. And someone, Amazon, should have used the RPKI rower with a max length parameter, and this attack wouldn't have worked so easily. The more specific attack would have failed. So some basic defenses would have worked, but none of those were in place. 2 hours later, a huge amount of money went west. The lesson is that attacks are multi-structured. It's A, then B, then C, then D. So I'm not even sure that the routing attack was necessary at the start. If I can fool a name registrant and say, hi, I'm that party that owns that domain name. Can you put in some new NS records? Done. All over. It's my DNS you're now consulting, not the original one. Oops. And if I manage to do that, I can sign the name with my DNSSEC. I can go to a certificate provider, such as, say, Let's Encrypt, going, I'm real, give me a real certificate, and I'm in. Doesn't even bring up a fake certificate warning. So in some ways, there are all these weak points because the internet has so many components. And when you go to a website, you're trusting all of them at once, every last one. You know, I could just fool a CA's automated test to get a fake certificate. I'm like, no one delivers these things by hand. So I attack the DNS. I start to provide fake answers. I go to a CA, give me a certificate. I get a certificate. Then I attack the routing system to go to my web page. All over, I'm in. So attacks are not just attacks on routing. They're attacks on vulnerable parts of the infrastructure. But sometimes, most of the time, there are all the rest. You see, you're professionals and you make mistakes for a living. It's what we do, and we're really good at it. So when we look at some of these BGP routing anomaly monitors, here's Cisco's one, BGP stream. There are a few out there. And what you see is an endless litany of things that went wrong because routing is hard, the interfaces are complicated, And the folk who are manning the keyboards over in the op center aren't being paid $1 zillion trillion an hour. Quite the opposite. And so what we find is that, you know, the quality of the work that we get out of these is considered at a global level problematic. Also, routing is complicated. Configs are complicated. Making incremental changes to a router, oh, I'll just change this filter list over here. Oops, the world's gone black. It's happened to me, probably happened to you. It's happened to all of us. So yes, we get routing wrong a huge amount of the time. We don't need attackers to get it wrong. We do it to ourselves. As I said, we're professionals. We're really good at this. Now, it's not that this is deliberate. Oh, I think I'll go to work and make a global routing attack today. No, 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 no. We'd all like to do a better job. And even when we consider the design of these systems that we're trying to do, and there's a fair deal to think about, if you're going to build a better routing system, what's the typical attack that you're trying to defend against? And so the process that started, geez, in this case, about 15 years ago, took at this protocol attack. What's a good example? There it is. Had to say it. You can't talk about routing security without talking about Pakistan Telecom, Reach, and YouTube. You just can't. And this is the typical BGP incident. It's a long time ago, 2008. Maybe some of you in the room weren't born yet. I don't know. I guess you know the details. YouTube was announcing a /22. Pakistan Telecom, which was trying to stop YouTube access in Pakistan, announced a /24, more specific. They were only going to announce it in Pakistan, but, you know, bad things happened. It leaked to Reach. Reach is a regional transit provider. It learned it from Pakistan Telecom. No filters, more specific. Everyone learns it. Yay, YouTube gets turned off. Now, what's the failure? Well, oddly enough, while you might say Pakistan Telecom had fat finger syndrome, and that was a really stupid idea, the issue was too that Reach weren't filtering. I shouldn't learn that route from a customer. I should be learning it from my upstream, says Reach. But no, 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 no. They were prepared to believe Pakistan Telecom when they said, I've got some Google property over here, route through me. So filtering failed. Because while some ISPs actually do a really good job of maintaining and applying filters, out in the wholesale internet world, where wholesalers get a whole bunch of ISP customers, filtering is something, well, you just don't do it, do you? This sort of false route just propagates around the world because right deep in the middle of the network, trust replaces good engineering. Oh, you're doing a good job, why should I? The good job is being done, right? Wrong. So 14 years ago, we've learned a lot since then, haven't we? Again, we're professionals. Twitter, oh dear. February 2021, oh dear. Myanmar, there goes a more specific. It propagated 104.224.42. Oops. Now, Twitter had actually gone to, you know, the RADB. They'd put in their RADB entry. This is me. Don't believe anyone else. But, you know, Myanmar, everyone believed that it propagated outwards. It hit a few of the big transit filters, the transit networks, and about 40 other ASs who say, well, filtering's not my problem. So we're not getting any smarter, are we? We're really not. Now, this whole idea that route registries will save us if we all just did it right is even older than those incidents. This was part of the National Science Foundation's NSFNet way, way back when I was young in the early 1990s. The problem with routing registries, which is a commentary on routing, which is normally maintained by people. And so this initial enthusiasm, I must fill out a route registry entry, I must keep it up to date, becomes, oh, it's a Friday. What am I doing? Squirrel. And just, they lose attention. They require intense feeding, watering, weeding, or else they just die in the jungle of bit rot. And most routing registries have more crap than reality. And the problem is there's no bit that says, this particular entry, don't believe. Because it doesn't flag itself as bad stuff. The good stuff and the bad stuff are just shuffled together. You can't tell. So the less respect and attention we pay to them, the worse the entire system uses. And you might say, I'm different. I do a much better job. And you're probably right. But from the other side, me, the user, the reader, how can I tell someone who's not looking versus someone doing a really good job? It's just a routing registry entry. You can't. So we wanted something better. And of course, as soon as you say that, in come the crypto scientists. Use the awesome power of digital cryptography. We will just automate the heck out of this. Get rid of all the humans. None of these hand-created lists, no human operators. This will just work perfectly. You know, this is blockchain for routing. Yeah, we're over there. Now, at the time, there was a kind of weird marriage of convenience because if anyone's ever used Whois, and most of you have sometime, and you think about it a bit, open protocol, it's just ASCII. Anyone can intercept and supply the answer. It's as bad as DNS over UDP, to be perfectly frank. And quite frankly, why should you believe it? Is because I asked the right IP address, I get the right answer, a credible answer in today's world? Of course it's not. You know, should I believe everything the DNS tells me unless I do DNSSEC validation? And the real answer is you really shouldn't. That's really stupid. It's not just credulous, but the ultimate point of credulity. It's just crazy. So we're aware of this over in RIR land. We wanted something better. And what we really wanted to do, oh naivety, was sign Whois. This is our answer. And you can check that it's our answer, not just someone who made it up and intercepted your query, because we've signed it. And if you use our key to validate it, this is us. And because we've signed it, and because you validated it, we actually don't care who you ask. You could ask anyone, it's good stuff. So we did this for addresses. We produced a PKI that allowed us to certify addresses and say, this is good. It's the real deal. This party who owns the key can speak about these addresses. That was a registry problem. The BGP folks said, let's use it for routing. Now, routing has two problems: how you inject information in and how you propagate it outwards. Origination is the original injection. And we used a thing called routing origination attestation. Is this a real route? Well, let me look at the cryptography. 35% of the internet's address space in V4 is now protected in this way. That's pretty good. In Australia, it's up to 60%. In New Zealand, it's only 45%. We're winning, yay. But signing is not using. So, you know, we need to assemble all this and figure out their propagation and drop all the routing announcements that are invalid in that way. Using is just a little bit harder. Propagation is difficult. Around the world, 16%, that's what, 1 in 6 or so of users won't go to an address where the routing information says, that's bad. You are being deceived. It is really bad. It's not just there's no credentials. What credentials there are say, this is a lie. Only 1 in 6 will not go there. Because of Telstra in Australia, you can see when they turned it on, and you can see a whoopsie or two through the years when bits and pieces of their edges stopped doing filtering. But on the whole, around 65% of users in Australia, if they're using the right ISP, will not go to a bad place. In New Zealand, the story is a little bit more chaotic, but it got turned on earlier this year, and it's now at around 45% of users. Again, Australia's winning. Yeah, right. But propagation is hard because in some ways, not only do I need to detect the origination is good, I need to actually ensure that the AS path is good. Otherwise, it's really easy to lie. And the problem is the only approach we used to protect the AS path is dead on arrival. It's so crypto intensive. The deployment approaches are not piecemeal. You have to build out connectivity. This is the IPv6 transition made worse by about 100 orders of magnitude on steroids. So if you think IPv6 20 years later is just coming, BGPsec, that train is never coming. it's just dead. So quite frankly, BGPsec, actually partial deployment's worse than none at all, as far as I'm concerned. So, you know, this is not working too well. Oh, and by the way, even then, it's only a partial answer because routing is backwards. You tell me something about the forwarding path I have to use. So the AS path is not about the path to reach you. The AS path is the path the route advertisement followed. And it's not necessarily the same thing. I have traffic for you. I actually don't care as much about how I learned about the route to reach you. I really care about the forwarding path. Can I hand this to someone who is going to get it to you eventually? So oddly enough, we're not securing forwarding. Securing routing is one step removed. And then we just hope, you know, literally hope that routing is accurate without any reason to understand why. So the whole thing is actually an article of faith. So let's see how well this works in practice. Let's look at some more examples. And of course, I have to use Facebook. Oops, sorry, I have to use Meta. October last year, they locked themselves out of their own office. The facilities wouldn't open. Why? All their name servers were in a single routing prefix. That routing prefix died. No one could find it. And of course, because they're oh so intelligent, they use really small TTLs in their DNS. So when the DNS went offline, they went offline really quickly. And it took them 6 to 8 hours to get back. If the 5 nines world gives you 5 minutes per year, Meta just used 72 years of credit in that particular outage. And they managed to impact 3 billion users who use Facebook. Well done. That's a professional job. So yes, it was an own goal. Wasn't an attack. Wasn't even an internal operational error. And quite frankly, this inadvertent route withdrawal isn't even protected. You're out there on your own. The DNS amplified it and everything went bad. Fastly, well, that was actually a platform crash in Varnish. What's Varnish? Well, it's a Danish a Norwegian newspaper content management site. That was actually mixing customer and provider configs. Akamai, load balancer problems, not routing, load balancer. But this whole thing about own goals and collateral damage, they are insanely common. Someone in Nigeria in 2018 leaking Google Cloud routes. And because it worked so well and everyone believed him, 2 hours later, they leaked Cloudflare routes as well. Yay! Would RPKI have helped? Not at all. It wasn't an invalid protocol. It was just a customer announcing transit links learned from one transit to another and the other people believing them. So it's a policy violation, not really a security incident. This happens a lot with load balancers. If you're using Noxian's BGP optimizer, think hard, think very hard, because those synthesized more specifics can be a real problem. And, you know, huge amounts of traffic gets redirected along mule tracks and everyone has a hard time. When all of Amazon, all of Cloudflare goes down your customer link, you're going to die. And so is Amazon and Cloudflare around that area. Would RPKI have helped? Yeah, possibly, possibly not. Depends on max lengths in ROAs. IBM is not immune. Again, would it have helped? Yeah, maybe not. Time Warner Cable. I'm like, the list just goes on and on and on. Oh, and yeah, a bunch more Vodafone India. They're all avoidable if you really, really were retentive about ROAs and max lengths. But as we see, not everyone even does those checkings. And there's another problem with ROAs. They're all of the internet all at once. But my policies are, well, in New Zealand, I want something. In New Zealand and Australia, I want something else. And globally beyond that, I want to use particular transit providers. The way you balance the way you spend your money in routing is actually context specific. The way we do routing security is not one rule for everyone. But I don't fit. Tough. Sucks to be you, one rule for everyone. And so some of these things are, the design is wrong. We haven't actually managed to accommodate the diversity of routing policies. So when we get policy breakage, we get breakage. Does network automation help here? You're about to hear from Richard later this afternoon that network automation helps everything. It doesn't. The issue is that now you've got control over your entire network all with one keystroke. And that is a good thing and a bad thing. There is no margin for error anymore. A huge potential for that keystroke to unleash mayhem. And of course, with automated scripts, once you've done it, it's very hard not to. Some network managers have seen, the purchase of these automated systems as a complete substitute for having skilled network operators and skilled and careful design engineering, which, as I say here, is a stunning triumph of unwarranted optimism over the harsh realities of just exactly what these systems can do and what they can't. And if you think the answer is AI, I want to live in your universe, but it's not the one I'm living in. That's not an answer. And does RPKI help? If you take a highly complex system and add more moving parts, you've actually got a more complex system that's actually got more points of vulnerability. It doesn't make it more robust necessarily. This whole idea that one rule set to apply globally doesn't actually match with what we want to do. And most of the route leaks we've seen are policy violations, not just BGP acting up. And quite frankly, the whole thing about a distributed protocol and synchronization, we've seen routes in BGP that are true ghost routes. The people who originated them have long since withdrawn them, but they're still out there because the withdrawal didn't propagate as far as it should. We don't even know what they are. There's all these issues in the routing system, and you kind of think, can we make this secure? Well, yes, but we're a long way from that goal. So the route set in V4, it's up to a million items, but the clue set is finite. It's not doing very well, and automating it doesn't really make it better. This system is brittle. How can we make it more robust? As Mike O'Dell said 22 years ago, if we knew what we were doing when we started doing routing, we wouldn't have done it this way. We really, really wouldn't. If we thought about it, it'd be too scared to try. That applies to the DNS as well. If we thought about that, we'd be too scared to try. So what I want to leave you with is this message that I'm not saying don't do it, but I am saying you're at the bleeding edge of technology. We are trying to understand what the problems are here and how to solve them. So operationally focused incrementalism, be very careful when you deploy it. Be conservative. Don't think it's going to save you from all kinds of badness. It won't. What we actually need, clue, is actually more engagement from the research community. What we actually need is more experimentation and understanding of the properties of the routing system. And to make that happen, we need buckets more research funding. That's really where all this will actually do some help and make it better. So I've left hopefully just 1 or 2 seconds for questions, and I will hand it back. Thank you very much for your attention. Thank you.
Hi, Jeff. You said that BGP-SEC is basically dead, and I agree with you. But why are certain personalities within the routing security arena trying to push BGP-SEC again?
The dear old US Department of Homeland Security, DHS, has a huge budget. And often they spend the budget on folk who are saying, I can solve your problem. And so there's a certain amount of vested interest in claiming that technologies work when in actual fact, they're lying on their back, legs in the air, howling at the moon. And BGP-SEC is lying on its back, legs in the air, howling at the moon. You don't have the routing hardware to run this. You really, really don't. And if you think it's a good idea to put all your private keys on an unmanaged automated computer system, good luck to you. I wouldn't. And so the design, the approach, DHS is impatient. They want a rock solid security in their internet system to protect themselves from bad people, and they want it yesterday. And they kind of, why not? Why not? This is easy, make it happen. And so folk who want their money say, yes, I will make this happen for you. I will deliver. Just don't look in the box, is all I can say. Just don't. It's not a pretty picture. Naming no names.
No other hands up in the room? No, that's us. Thank you very much, Jeff.
Well, thank you very much, and thank you for bearing with me in this virtual world that I still inhabit. Thank you.
Great. So next up, we've got Aaron from RANs, and just follow up on Jeff's talk. He's going to be talking about securing the internet with RPKI.
So I got to say, it's a really nerve-wracking experience following Jeff, because you never know if he's just going to have systematically dismantled your presentation. So I think I got off lightly, I think. Yes, so I'm here to sort of do a bit more of an operational talk about how to turn RPKI on. You all heard Jeff, he said you should do it probably. Yep. Do I have to point it at anything? Okay, there we go, it's gone back. Okay, a little bit about us, just because we're quite small, which sort of makes it easier to do these sorts of things. One of our engineers sort of took this on as a bit of a pet project, and sort of did it over the couple of months, and then sort of told us the next day that he'd turned it on. No, that's not quite how that happened. We're not quite that cavalier. Anyways, let's talk about the problem. Jeff went through this a little bit, but I've got some diagrams here about how this sort of works. It's actually really easy to hijack other people's address space. All you need to do, as you can see here, is just advertise more specifics, and the internet will believe you. And you'll get all priority, and you'll get all traffic from across the world. You don't even have to advertise more specifics. You can just be a bit closer to people, and then they'll probably believe you and send traffic to you as well. So you probably won't capture the whole world at this point, but you'll capture a good chunk of people, and you can put yourself in a specific position and you know, capture traffic from people that you're targeting. It doesn't have to be malicious. It can be accidental. We've seen, you know, many times where people have paired with people and then paired with other people and got in the routing policy really bad and just transited traffic. Usually it's not the end of the world, but it is a bit of a security violation there. So what mitigations do we have? And actually, I just can't even talk to this slide because Jeff put it so well in his presentation. Basically, we can do IRRs, and we do IRRs. But, like, you know, what do you believe? As Jeff said, there's a lot of cruft in there. There's not really a good mechanism for ensuring trust, although the RIRs have put a little bit of effort into that by basically presenting an IRR information inside of their web interfaces or inside of their APIs. So we're better, but it's still not great. So, oh, and don't get me started on writing routing policy based on IRR information. It's I don't trust it. So RPKI. Just a little bit about it. Obviously, we've been through it a lot. One of the reasons why we went down the RPKI route is we were sort of looking at what we could do to gain manners compliance. And actually, it's not strictly required for manners compliance, but it was recommended, which sort of put us onto it, and we decided to give it a bit of a go and see what happened. And as it says, all it does is it cryptographically binds a route prefix to an origin ASN. And all of that information is stored inside of your local RIR. So because I am the sort of person who reads books for the pictures, I have sort of made some pictures about how our RPKI works and what it will protect you against and what it won't protect you against. So we'll go through it nice and slowly. So what does RPKI protect us against? there's a guy, shows up, wants to enter the party, and the bouncer there asks for his name, Jamie. Now, I just want to be clear here. I'm definitely not poking fun here at a person that we probably mostly all know who actually got married on NZNOG weekend and then proceeded for the next decade to drag his wife along to NZNOG for their anniversary. Yeah, he realised afterwards that was going to be a thing. Anyways, Jamie, from Wellington? No, from Sydney. Sorry, buddy, you're not on my list. So RPKI will protect you, another ASN, from advertising your routes. So next thing, what else does it protect you against? Can I join the party? Same conversation. What's your name? Jamie. From Wellington? Sure. Jamie Senior. So this is a little bit of a stretch in terms of what it protects against, but this is the best I could come up with at the time, so I'll have to apologise for that. Jamie Senior? No. Jamie Junior? Sorry, buddy, I've been specifically asked by your dad to not let me in. So RPKI will protect you against the same or a different ASN advertising a more specific route, which is good. What doesn't it protect you against, as has been mentioned many times before? Can I join your party? What's your name? Jamie from Wellington? Sure, why not? It's good enough for me. So RPKI will not protect against malicious parties forging your ASN as the origin, which it turns out is really easy to do. So TLDR protects against accidental advertisement of incorrect routes, protects against route hijacking with more specific routes. So that is the ability to basically draw traffic from across the world towards you. But it won't protect against someone impersonating your origin AS and advertising a route of the same length. And it also won't protect against accidental transit of peer routes because the origin is still correct at that point. And as Jeff said, it's actually really hard to protect against those problems because it is an AS path problem. Although, as I hadn't thought about it before, as he pointed out, it's not actually really a route path problem, it's a forwarding path problem. So I hadn't thought about that before. Okay, so let's go through, because there's an operational talk, let's actually go through what an RPKI implementation actually looks like. So it's actually not too complicated if you don't, if you stand at a really high level, which I like to do, and look down upon the thing. It's actually only got sort of three main parts to it. There's the rowers, which are the information that you configure and is all stored inside of your RIRs, your regional internet registries. You've got your validator, which sort of unlocks those rowers, and then you've got your routers, which make use of that routing information. So the rower, how does it work? It's pretty simple. You've obviously probably all got your whois information already in your My APNIC portal. All you need to do is just tick that rower button and it just works. Then there's the second thing, your validator. And this is the thing that basically downloads all rowers across the world and unlocks them and turns it into sort of routing policy. So we use Routinator 3000 for this. Actually, in the past, we had used the RIPE validator, which was a Java application, which was very, very, very memory hungry. It used about 6 gigs for each of our containers that we used to run it on, which was, our sysadmins were happy when they got that memory back. Yeah, Routinator is quite good. It's really easy to deploy. The one thing that we really liked about it had an inbuilt Prometheus exporter, and we're doing a lot of Prometheus in-house. And it does everything you expect. APNIC here does have a really good blog on the installation of a number of different types of RPKI validators. So if you're looking at it, I suggest you go and have a look there. We actually followed those instructions and it worked pretty well for both the RIPE validator as well as the Routinator validator. This is information that we've pulled out of that Prometheus exporter, that Prometheus endpoint, which just shows sort of the number of rowers that we're learning and unlocking. This number is actually about 3 times higher than the first time I gave this talk at Apricot in 2020, so we're probably going in the right direction. Either that or everyone's just advertising more specific rowers, who knows. Cool. So, once you've got that information unlocked, you need to ship it off to your routers. And to do that, you use the RTR protocol. It actually has a number of transport types inside of that RFC. We use the unencrypted one because that's the one that's implemented everywhere. There are other organizations, maybe more cloud scale organizations that go, we don't want to run all of our routing information across our core unencrypted, and that's perfectly fine. You can do other things like split that up and basically have your RTR talker quite close to the edge and just run sort of encrypted APIs out to your edge and plug directly into a box at your edge and talk RTR at that point. But as you can see there, we're a Juniper shop, so I've chucked some Juniper config in there, but it's really easy to turn on. One thing that's not in here is make sure that you add that protocol to your firewalls. Cool. So how do you enable your RPKI policy? It's actually really simple. All it is routing policy. You just point it. Validation state is just a table sitting on the box, and so routers are actually really good at looking up routing tables, so it's really easy to turn on. As you can see there, we are accepting unknowns. You don't want to drop unknowns because that's still about 60% of the address space, so you'll drop 60% of the internet if you turn discard on unknowns on, so don't do that, accept them, but accepting unknowns is basically just keeping the current state of non-RPKI, so you're not in any worse position by accepting that. As you can see there, we are rejecting invalids. We didn't do that immediately. I suggest you don't just reject invalids without having a look about what's actually going to disappear. But have a bit of a squiz through and then maybe turn it on and see what happens. For us, we have a couple of best practices that we did. We have only turned it on in our external BGP feeds, so that's peerings and transit providers. We haven't actually turned it on for our BGP customers. The reason for that, and we are intending on doing that at some point, but the reason for that is we already have a strict routing policy on them. Basically, we've got an IPAM which has all of their routing information that we build strict route filters that are exact route filters that we accept from them. So that was sort of more strict than RPKI would be, so we didn't bother about turning RPKI on for them, but we might do so in the future. Well, we probably will. Begin, as I said, by logging invalids. Don't just drop them straight away, because if you've screwed something up, you could actually drop a lot of your internet connectivity. And then eventually, once you're happy that you're not going to lose too much that you care about, act on RPKI validation by turning invalid reject on. We also use exact prefix lengths for our rows. The reason for that is if you don't, it becomes really easy to hijack your address space with more specifics. So we use exacts so that at least if people try to impersonate our origin AS, they can't. They probably can't easily draw away people that we directly pair with, which tend to be the people that we care about the most. And we actually automate regular checks of our configured rowers to make sure they're right. The last thing we want to do is have people not be able to talk to us because we've made a mistake. Humans make mistakes, that's what they do. I do it on a regular basis, even though I try to deny it. And so, yeah, we basically look at our IPAM, which basically says what should be advertised, and we compare that to what... and so that IPAM is used to generate all of our routing policy about what we export and everything like that. So we basically build a check to see what comes out of the rower APIs to see that what we have in there is what we expect based on what is in our IPAM. Should I enable RPKI validation? You actually get benefit. So benefit, you get it immediately as soon as you turn it on. And it improves as there's more adoption across the internet. So it's not like this, everyone has to be on it for it to be useful. You do gain value in it by just turning it on straight away, and the value just increases as we get more adoption. yeah, performance and reliability is completely unaffected. All it becomes is a BGP lookup. Routers are really good at that. The failure case is actually really good. What happens if you stop being able to talk to, say, the RIRs and downloading rower information, is everything just over time reverts to unknown. And as soon as you've got, and while you've got unknown as accept, all you're doing is reverting to the status quo anyways. So you're not going to, you know, if your validator falls over or if you stop being able to talk to the RIRs for whatever reason, you're not going to end up with this case where your entire network just falls over. And operationally, pretty simple to set up. Most of the hard yards is getting the validator working. And as I said, APNIC have got some really good documentation on that. Cons, obviously, you've got to ensure your rowers are kept up to date. You know, we've got a script, as I said, that does that regularly, does that check regularly. And it's a little bit of extra training for the NOC. One of the difficult things is when you run into a problem, you know, someone comes to you and says, look, I can't reach you, or I can't reach a customer behind you. You immediately start looking at routes, and then you go, but you're not sending me your routes. And really what's happening is they are sending it to you, it just never ends up in your routing table because RPKI drops it. So if they have, you know, an invalid that you're dropping it on, it can actually take a little bit of time to realize, well, it took me a little bit of time to realize that it was RPKI dropping it, and go back to them and ask them to fix their rowers. I'm sort of going back on this a little bit, actually. I was originally of the view there's not really any point in turning on RPKI validation if you receive a default route, because if you reject an invalid, all you're going to do is you're going to fall back to your default route, ship it to your upstream, and they'll ship it to the people anyways. But actually, when I first wrote this presentation, our upstreams didn't do RPKI validation. And so they've since turned on RPKI validation, and all of those problems go away, although we don't receive a default route. But as sort of the tier ones and things start to turn on RPKI validation, actually there probably is still value in you turning it on, because you're still dropping invalids across exchanges and things that you're connected to, and in particular customers as well, if you're turning it on for customers. So since we first turned it on in late 2019, I think it was December 2019, we have had 4 reported faults. I think it's 4. I don't really remember. I've dealt with 2 of them, is all I know. It's not too bad to chase it up. People will get in contact with you and say, we can't access your services or your customers. Eventually, you figure out it's RPKI, you go back to them and ask them to fix their rowers. It wasn't too bad. It's probably taken, I don't know, it was 3 or 4 hours from report to getting them to fix their rowers the last time I did this. So lessons learned, always keep your contacts up to date, so who is and peering DB and whatnot, so that if you do run into a problem, people know how to contact you. As I always say, automate checks of validity of your rowers. Humans make mistakes, so it's much easier to add extra belts and braces there to make sure you've got the right thing set. So you don't actually need to implement a check of what IP space will disappear, because the RPKI Observatory actually has all of that information and will tell you by AS what route should be invalid. But it is worthwhile going through and having a look at that and seeing if there's anything in that list, which is about, I think it's about 1.5% of rowers are invalid. So having a quick look, seeing if there's anything in there that you're really desperate to keep connectivity to before you actually turn on your discards. But apart from that, it actually wasn't that hard to roll out. We didn't run into any drastic issues with having it running, really. I know there is research coming out about ways that you can actually DOS people's RPKI systems. I'm not going to touch upon that. I've kind of buried my head in the sand a little bit around that because it's complicated, and I'll wait till the researchers come up with all of their findings and give me a recommendation. But yeah, highly recommend actually working towards it. I think there is a lot more people now that have actually turned RPKI on, but there's still plenty of you that that I'm sure have not. But let me just encourage you, it's not very hard. It's probably a couple of days work if you want to do it carefully. But yeah, it just kind of works. Cheers.
No hands raised at all? No, you let off lightly.
Cool.
So for the final talk of this session, we've got Conrad and Noel from Arista to talk about 800 gig and beyond.
Hi, my name's Noel. I'm a systems engineer working for Arista Networks. The presentation today is about 400 gig, where we're currently at, and then moving up to 800 gig. Conrad will be covering 800 gig, and I'll sort of cover the 400 gig technology, sort of where we are at the moment, and what the future looks like. A lot of you say, oh, we won't need 400 gig. Trust me, you will need 400 gig. So just to cover off some industry standards, this is a quote of a colleague of mine who presented in India at one of the NOG communities over there. The easiest way to go faster is go faster. Ethernet speed transitions have been the primary driving force to improve throughput and the price performance of service provider and data center networks. It's very true. You know, we're over the era of QoSing our network, making sure that every single packet gets counted, most available bandwidth, just make it faster. So the technology ramp, where we started, 100 gig, 10 gig, 100 gig, 100 gig was the big thing back in the day. Then we're sort of getting speeds onto 200 gig, 400 gig is now sort of rearing its head, and it's been adopted quite widely, especially in data center spaces, short distances where the optics can be managed. The driving factors behind it, a lot of it 5G, data center, of course, cloud computing, high definition video, cloud native OTT applications. It's a story we hear all the time. These are the things that are driving capacity demands on networks, and also the things that we need, obviously driven by technology as well. Market trends, product standardization. So going into the 400 gig side, we see that you know, this is becoming very standardized. You'll see later on in the slides. And the adoption rate now going forward is going to ramp up significantly. So yeah, it will replace, 400 gig will replace 100 gig, 200 gig faster than 100 gig did other Ethernet technologies. This is sort of predicted. Okay, what are the challenges that people are facing that will drive them towards 400 gig? So more bandwidth, of course, it's always the story. Distributed services across your data center, across your network, where you need more bandwidth in between these applications to be able to communicate. Annual growth rates, you know, more demand, and then cost of power versus bandwidth. Time for big stonking machines in the data center and in your telco networks are coming, you know, they're running their course. Everything needs to be power efficient, and the cost of that must be down. And then also one thing that they find is driving the moving into obviously new technologies like 400 gig. Optic availability is also very limited. The on-ramp, the manufacturing, the development of that is slow. So that's also one of the challenges that they experience. So increase network speed, reduce power and cost, and expand capacity. That's sort of like the position that we're at now. So, as you know, in the market we have short-range optics that are available now that are being used within organizations' data centers. So I'm going to be covering off more of the 400 gig ZR and ZR+. This is sort of the longer range, extending beyond 10 kilometers, the LRs. So drive up capacity and cost per bit down. As you can see from the 100 gig, a lot of people or a lot of service providers, a lot of organizations are reaching the Shannon limit. Shannon limit, I actually had to look it up to see what it was, to understand it. So it's the maximum you can get out of a limit without any errors within a sort of a capacity range. So with 100 gig, a lot of people are using that. Now what's happening is people are starting to bundle 100 gigs into 200, 300, and that's obviously brings that limit down, but then the onset of 400 gig drops that rate really low. So multi-hall DCO and open ZR and ZR+. So these are where we're developing coherent optics within the the need for metro-based data center interconnects and cloud applications. So target use case comparison from the data center into the telco side. So the key thing within 400 gig within the data center is the dollar per gigabit that you drop down with inside there. And then on the telco side, the use cases, transmission links going up to 400, the edge is also part of this, data center to edge, and then of course, the metric that we measure that with is dollar per kilometer. So why? Why are we transforming into 400 gig ZR? So DWDM designs were proprietary. I say were, a lot of it is changing. This committed vendor lock-in, good for vendors, not good for customers. The 400 gig ZR implementation is now standardized by OIF. This also opens up the door so the vendors can compete with one another and also have input to say into the optics. And then competition changes, of course, if everybody's part of it, it drives the cost down because there's not a monopoly on it. So what is 400 gig ZR, ZR+? So multi-vendor DWDM standard. It's a coherent tunable optic. Supports speeds 400, 300, 200, 100. Dense client form factor. So no need, you can plug these into your routers, your switches. Supporting 4.4 terabits per 1 RU and very low power, like 20 watts of power for ZR+. So there's currently two standards of 400 gig out in the market. It's OSFP and then OSFP DD. So OSFP, it's sort of just an overview of what the optic is. This is also for the data center standard, but more, it sort of covers both areas for the optic type. Just some key notes of this, it's 20 watt power envelope for ZR+, and then supports 400 and 800 gig, and then with the 60 pin AUI, with the new silicons coming out, the faster silicons, the bandwidth will be optimized to be able to support that. And again, 28.8 terabits with N times 112 gig SerDes, which gives us 36 by 400 on 1 RU. So it's a lot of capacity in a little small box. Now with the OSFP, it gives us opportunity to move from 800 gig, 1.6, 3.2 terabits. There's a roadmap mapped out for that, and Conrad will cover that for us. So QSFP DD, also, this is just the OSFP that's has to be plugged into an OSFP port on your hardware device, whatever device you have. QSFP-DD is a QSFP standard that will just plug into a standard QSFP port, but there are some limitations on it. It doesn't have a clear roadmap beyond 800 gig. There's obviously still a lot of development on that, but it can support, also up to 28.8 terabytes. So there's a lot of fighting, or not fighting, but there's a lot of discussion within the industry, QSFP-DD, OSFP. So, there's a lot of forums and people taking part in the discussion. Which one will win? We don't know. Which one will be the preferred? These two optics interoperate with one another. So you have an OSFP on one side and QSFP-DD on the other side. They will communicate with one another. So while pluggable form factor. So modules directly into the hardware devices. So, and you can also source them directly, no margin stacking by a third party. Again, one system design, no extra investment required to deliver DCO. And you can mix and match DCOs from your line systems into your client optics, and then multiple SKUs expected for 400 gig further. So you could see the ranges are extending as they get smarter and smarter in how they develop the optics. So the ZR TX power is low. Transmit power is low. So if you have a legacy line system, you take this thing or the ZR optic and you plug it into your line system, you'll obviously have to see if your line system supports that. So mine is 10 dB waves. So we'll say it requires dedicated amplification. So the amplification does not necessarily have to be a true line system. It can be something that can give it amplification. So replace DWDM transponders with 400 gig ZR modules. So this small form factor device will, eventually be able to replace racks and racks of hardware. 400 gig DWDM inclined form factor, like I said, you can plug it straight into your hardware device. OSFP port, tunable over full C-band, open standard, and most cost-effective DCI transponder. So it requires amplifiers, not a full line system. It doesn't have to be a full line system like I mentioned. DCI reach of 40 to 100 kilometers, and dark fiber from 0 to 40 kilometers about. You won't need any amplification. So this is not a plug. I'm just showing you a demonstration of taking a complex line system, how you can simplify it into just a few pluggable optics into your hardware. So what we have is an OSFP line system. So this line system is the amplifier onto the dark fiber, essentially. All traffic coming between the two transverses through the OSFP LS. And then it gets pushed out onto a 8-channel colorless mux-demux system, okay? And that is 8 channels of 400 gig. That doesn't have to go into the same system. You can distribute it across various platforms. So it's just the power or the cost of powering your hardware devices, and that's it. The OSPF LS just gets its power from the device and its management interfaces on the hardware device. So this is sort of where the industry is going with this now. Just to give you an insight to what it is or where it's going. So just to summarize, 4 times the bandwidth of 100 gig Ethernet, power efficiency, twice power efficiency, twice the price performance, bigger pipes, less stuff to manage, take away the pain of load balancing algorithms on your backbone with lag, etc. Like it's busy and will be revolutionizing the optical transport, price performance and density. Like the hardware devices will be supporting 400 gig ZR and ZR+, And the optic modules will support full power for 400 gig ZR+. So plus feature, that's 800 gig dual 400 optics that are fully compatible with 100 gig lambda optic ecosystems. So this is just sort of to give you a brief view. I know you're sitting there now saying, oh, I don't need 400 gig, but mark my words, you will. Like I said before, it's the way things are going. And yeah, let me hand over to Conrad and he can cover off 800 gigs and what's happening in that.
Thanks, Noel. Yeah, absolutely. It's the same discussion we have with customers have through the years. Oh, I don't need 10 gig, I don't need 100 gig, I don't need 400 gig. And now I'm here to talk to you about 800 gig and 1.6 terabit and even 3.2 terabits. Well, the truth is I'm really just a geek and I'm really into these things. It may be years before some of these things come along in New Zealand, although we've already got 400 gig deployments out there. So let's have a look at what's going on with the transition from 400 gig to 800 gig. And we'll start by looking at kind of what's happening with the pluggable optics. We've seen the migration through SFP, QSFP, and now into OSFP and QSFP DDs. And effectively, these optics are made up with an electrical interface. It's a number of lanes running, and each electrical lane runs at a certain speed. So 400 gig is based around 8 lanes running at 50 gig. And with 800, what we're just doing is still running 8 lanes, but ramping that up to 100 gig. And then further to 200 gig with the 1.6 terabit optics. And we're actually expecting a very rapid take-up in moving to these 100 gig lanes, or SerDes is the other term you might see, serializer and deserializer. And looking at some of the analyst reports, the 650 group expect a very quick migration to 100 gig lanes from the silicon and the optics that we're seeing out in the market. In fact, in 2023, we expect to see more bandwidth delivered on 100 gig lanes than the entire bandwidth delivered in 2022 in all form factors. So a very fast ramp. That's the blue, I'm not sure if that's working, but the blue graphs, components of the graphs up there. So a very quick ramp. And the 800 gig really is being driven by what's happening with those optics, the 100 gig lambdas, and also what's happening with the silicon that's driving the switches and router platforms. But the initial focus with the 800 gig optics is actually to break them out into dual 400 or 8 100s. And part of that is because we're in this interesting situation where the optics standards are actually quite a bit ahead of where the Ethernet part of things is. So the Ethernet spec has been completed, April 2020, it's been around a while, but we're not really expecting to see the silicon delivering 800 gig Ethernet for switches and routers until 2023. So in the intermediate term, breakout is a more practical application. So another sort of way of looking at why 800 gig, as Noel said, really, it's about driving lower cost, lower power, and being able to keep up with that silicon that's coming to support the switches and routers. Ultimately, we're delivering a lower cost per bit and using less power. Have a quick look now at the optics we're expecting to see in the 800 gig ecosystem. These are all, of course, subject to change, but these are the sorts of things we're seeing in the labs at the moment. At the top, we've got the coherent optics, so the ZR systems that Noel talked about, where we can use passive optical or active line systems, 100 kilometer reach. Also, there's a 10K version of the LR version. The next ones down are based around 200 gig lambdas. So shorter reach, but also the ability to break out into 4 200 gig connections using the quad SN. Then we've got the 8 times 100 gig or 2 times 400 gig breakouts, showing here in the yellow. So either a single fiber, dual LC is for dual 400 gig, or the MPOs or 8 by SNs for 8 times 100 gig. And we've even got a dirty old multi-mode option for you, 50 meters. So I mentioned that initially we're seeing a lot of the applications for 800 gig being breakout, so be able to deliver high density platforms, but then break them out. And so in practical terms, these are examples with OSFPs. There's enough cross-section on the front of the optic to be able to have 2 LC connectors, for example, to deliver our 2 400 gig connections, or 2 mini LCs. And for the 100 gig breakout, we'll see on the right-hand side, the same cross-section allows us to have dual MPOs or the SN MTC connectors. So again, being able to break out 800 gig connections out of these optics. And there are many vendors producing these optics. This is just an example from our lab. We've got about 6 different vendors listed there, so it's looking very promising in terms of multi-source, being able to bring down the cost of those optics and giving you plenty of options. So looking at the next step, 800 gig, great. Well, why don't I go the next step further and say, well, if I could take those 8 lanes, it's the same encoding system, and I can ramp them up to 200 gig per lane, then I can get 1.6 terabits out of that same optic form factor. And that's kind of the next step. There's a few things going on in this. I mean, the case to just double that lambda and the electrical lane speed is I'm delivering lower cost per bit, because it's effectively the same number of lasers and connectors and so on in an 800 gig or a 1.6 terabit optic. So I can reduce the cost, reduce the power, and it also aligns with the generations of silicon we see coming in the next few years, which are going to 200 gig lanes out of the silicon. So we're seeing around the 2025 timeframe, we're seeing vendors expecting to come out with 102.4 terabit ASIC to deliver switching. This, I've kind of just covered this a minute ago, but the point being that to go from 800 gig to 1.6 terabits, the same component count. It's the same number of fiber terminations, same modulators, same connectors. So we expect the cost per bit to really be driven down. And this is obviously good for customers and and carriers. So the 1.6 terabit form factor, the 200 gig lanes, we expect to see again a ZR optic, 1.6 terabit ZR optic, 4 times 400 gigs, so be able to either run that as WDM or break that out into 4 different 400 gig connections, or again being able to break out into 2 800s or 2 800s or 8 200s. The bottom 2 options there. So there's a few things going on around the 1.6 terabit stuff. There's still some standards work. One is on the electrical side of things and the OSFP. It looks like it's very practical. There's just a couple of minor adjustments, but that will be fully backwards compatible with the 800 gig optics. But really this 1.6 terabit stuff is tied to the silicon that we expect to deliver our switches and routers moving to 200 gig lanes. And I mentioned that's 2025. But we've got this situation where the optics will be ready to go next year. 200 gig lambdas, awesome. And that's going to drive down the cost of the optics. But the switching, the silicon isn't quite there. We're seeing the next generation of silicon platforms are still going to be based around 100 gig lanes. And we're not going to see that 200 gig lane stuff until 2025. So we've got a bit of a gap. So what's the industry doing about that? Well, what's happened is they've come up with this thing, OSFP XD. And fundamentally, it's the same thing we've seen with SFPs, QSFPs, and so on, where you put an extra connector in there to double the number of lanes that are going into the optic. So with this idea, in fact, let's just go to the next slide. We put an extra row of connectors inside that OSFP cage. And that means we can deliver 16 lanes into that optic. So it means we don't have to wait for the 200 gig lanes. We can use our 100 gig lanes. 16 times 100 gives us 1.6 terabits, in the current generation of switch platforms without having to go to I say current, the one next year, without having to wait till the generation after. It also bumps up the power capability to support those 1.6 terabit, long reach optics. And the other thing that now we've got 16 lanes into this connector, once we go to 200 gig per lane, we can actually deliver 3.2 terabits out of this OSFP. So when you put that stuff together, you get some advantages of this OSFP XD connector in that it matches these silicon platforms we're seeing coming out from different vendors. It's possible to deliver 32 1.6 terabit interfaces in a single RU or a single line card. And when we go to the next generation of switch silicon, 32 times 3.2 terabits in a single RU device. And we've still got that ability to use all the current generation of pluggable optics, coherent, all the different lambdas and so on, and the ability to swap and mix and match different form factors. So I wanted to cover off a couple of things about power. One of the things that's really driving the industry, particularly in the public cloud side of things, is reducing power consumption. The challenge we see cloud bandwidth growing 50 to 60% per year, and we're reducing the network power per bit 25 to 30% per year. So they're not quite keeping up. We've kind of got this situation on the left-hand side. We'll see here, we are reducing the number of picojoules per bit to send our data, but because we're doubling each step, the amount of power we need per module is actually going up. So there's a few things going on to try and improve that. There's process improvements going from 7 nanometers to 5 nanometers to 3 nanometers to 2 to blah, blah, blah. There's also been a lot of work on reducing the power required for the electrical interface between the silicon and the pluggable module. But ultimately, as I've mentioned, the power per bit we need on the switch or the router platform is declining, a factor of 2 for every 2 process generations. Same in the optics for the DSPs that sit in there. But because the capacity is growing, doubling each time, the power per module is going up. And we're starting to see, sort of 30 watts per module for a data center interconnect optic and 20 for a client optic. Now, QSFP-DD, OSFP, there's a couple of horses in the race. OSFP seems to be the one that some of the bigger cloud vendors are going for, and that seems to be driving volume. They're also slightly larger, which means that we can have more thermal, output from them. But yeah, we'll see how that goes. And there's more power reductions coming, as I've mentioned. So the final thing I just wanted to call out was a thing called co-packaged optics. And this is one of the sort of promises we've seen in the optical space. The idea with co-packaged optics is instead of having your silicon for your switch or your router platform connected via some electrical lanes to the pluggable module, you have a single substrate that's got the silicon for the switching or routing and the optic on the same substrate. Now, really the idea of this was to reduce power and a little bit of reduced costs. They talked about wanting to reduce, let's say, a 1U switch which was delivering 128 400 gig interfaces They wanted to reduce power by 20%, which is awesome. And there's been a lot of submissions from Microsoft and Facebook and so on to the OIF about doing all this stuff. And there's been a few prototypes out there. The challenge has been it actually hasn't really delivered the power savings. A couple of things have happened. One of there's been some optimization of those electrical lanes, saves about 180 watts per RU at the wall plate. And the other thing is that a lot of these co-packaged optics, they use an external light source, external lasers inside the your switch, if you like. And the extra connectors that are used to drive those through the modulators and to the front panel actually add a bit of loss. It ended up you needed to double the power of the laser in order to get it. So the guts of it is, although for a while we thought that we would have to go to co-packaged optics to get these really high density platforms, the 51.2 or 102.4 T platforms, we've solved the problem with pluggable optics, and it's actually pretty much a wash power-wise. We also have the benefit that because if we continue to use pluggable optics, we're not tied to having the same life cycle between the silicon and the optical platform. We've got benefits in terms of serviceability and so on, being able to mix and match different form factors or different coherent versus different lambdas, etc. So I just wanted to call that out. There's a whole bunch more information in a presentation from Andy Bichtelsheim, who's really into these optics. I've got a link at the end of the presentation that has more on that. So I'll finish with a couple of summary slides. 800 gig modules are real. We've got them in the lab now. Initially focused on breakout, 400 gig and 100 gig breakout. The next step we see are those 1.6 terabit optics based on the 1600 gig lanes that will align with sort of the next generation of silicon we expect to see next year. And then beyond that, sort of 2025, that's when we expect to see the native 200 gig lanes coming even further. And there is still a real focus on trying to drive power reduction. I know it doesn't sound like it when we talk about 33 watts per module, but price per bit is coming down. Price per bit and power per bit. And as I just mentioned there, the idea that we can decouple the optics from the switch or router silicon. That's particularly relevant. Here we've got maybe 2 years between optics being standardized and actually being able to deliver an 800 gig Ethernet or a 1.6 terabit Ethernet. So that's it from me, just to finish off with an acknowledgement to Andy Bichtelsheim, who provided me with most of the content about these 800 gig and 1.6 terabit optics, and a couple of links for further learning if you're interested in seeing some more, particularly about the co-packaged optics and what we're doing in that space. And there's a good blog post there as well. Thank you.
Any questions from the audience?
For me or for Noel?
Nothing that I can see there. No. Thank you, Conrad and Noel.
The question is, Noel described how the 400 gig optics were pushing the Shannon limit. How are you getting around that with the 800 and 1.6 terabit?
Right, so it's been a while since I studied the Shannon limit, but so effectively the Shannon limit is based on how many symbols you can have within a particular frequency. And so the 1.6 terabits, we're going to a new encoding mechanism that has 16 bits per symbol. So it's still only 100 gigabaud. But it's a better encoding mechanism. So although it's double the symbol rate of the 400 gig, I'm trying to remember, we can fit it into a 400 megahertz wide channel in C-band. Yep. Cool.
Thank you very much. So that brings us to our afternoon break. Any other homework, well, things we need to announce, Richard? No? So in that case, grab some tea and coffee, grab a bit of a snack, and we'll start back again at 3:30 on the dot. Thank you.
Okay, so it's giveaway time. We promised a draw on the competition. So we have Matt from Two Talk, who's going to do his thing.
I don't know if I can plug in here.
Can we have the HDMI?
Right, so yeah, I'm Matt from Two Talk. Some of you may notice a little kind of Squid Game kind of card in the swag bag. And yeah. So yeah, sorry about that. Yeah, basically I created a little game. We called it an NZNOG mini quest. I thought it was quite cool to share that with you guys. And yeah, I was just giving away a prize for people that called the number and answered the questions. Used a few different things like text to speech and speech to text. So yeah, if you had an accent, unfortunately, it may not have picked up your name too well, but we'll see how it goes. So I'm going to give away just one of these microchip routers. We'll get it delivered to you off Go Wireless. You may have seen it outside on the wireless stand before, but here we go. So Sean Fisher. Woo, is he in? Right. So there's nothing for me to give you physically here, but yeah. Yeah. I've got your phone number, obviously, so I'll get in contact and get the details off you. Sweet. Cool. Thanks, guys.
Barry has 4 more goodie bags, swag bags, cooler bags. They are actually cooler backpack bags, so you know they should be useful. If anybody has not got one yet, or has a colleague who was supposed to come but couldn't make it because they were sick, you can grab a goodie bag off Barry. Okay, so starting this session, we have Rich Bayliss. There he is. So Arista bookended the break, and Rich is talking about building virtual environments, I believe.
That's quite nice. Bit of a clap for me. Makes me feel a bit good about myself. It's the first time back in New Zealand in 2 years. I've missed the people, obviously. You guys are good people. I've missed the country. I've also missed your sense of humour. And by that I mean when Qantas QF 143 was coming into Auckland on Sunday, they played the video that said, you will be required to have 14 days of mandatory hotel quarantine. And everyone on the plane went, what? So, yeah, good one. You got me. It is 3:30 or 3:33 on Friday afternoon, so I will try to keep this as light as possible. My presentation is legal about choosing your own adventure. Who ever read a Choose Your Own Adventure book as a kid? Yeah, I did. I love them. And what I also found when I read them, I always put my fingers in the different turn points and was like, nah, I'm going to come back to that decision. I'm not sure that this is the right choice. Then you get your face eaten by a gargoyle, and then you go back and you say, that is the wrong decision. So there's a few of those. So firstly, let's have a little bit of a scenario. You stumble in the office. Maybe, you know, after this, people are going to go back to the office to do work, right? Yep. Stumble back in the office, and you say, and your boss looks at you over the video conference because they're somewhere else in their holiday home, and say, yeah, but you completed that design, right? Whoop, oh, that design. And you go, well, what am I going to do? Maybe I'll do it tomorrow, or I'll log into my lab device and get this done before I go find the NZNOG crew for some drinks. Or why not just test it in production? So let's go to page, let's start with page 48. No, I'm doing that wrong. No, there we go. All right, so using the 1980s historical documentary Back to the Future. So you say, I'll do it tomorrow, and then you realize tomorrow is a weekend. And yeah, no, you're not going to do it on the weekend, and you get fired. The end. Okay, so let's go back. What was the next option? Page 103, let's use the lab device. The most amazing thing about that previous prize giving away was when they actually showed that there was a website where they still had stock of more than 50 units of a particular networking piece of equipment. Like, I was just like, wow. All right, so let's use the lab device, and you sit there, your session doesn't work, and you say to yourself, well, why is my lab device not working? And you ask a few questions, and your mates say, well, we put it into production because there wasn't any equipment around. And you're stuck there with a US power cable and nothing else to test. The end. You are dead. Or the third option, let's test it in production, why not? And then you make the news tomorrow when you cause a network outage. Just reading the news the last week, I feel like a few people have been doing this a little bit. Yeah, you know who you are. Anyway, the end. So let's say what the goals are. The goals, we do not want to get fired. We do not want to work on the weekend. We don't want to have to wait for equipment, and we don't want to make the news. Pretty safe. So how do we do that? Well, firstly, every one of you is your own unique little snowflake, and I can't tell you specifically what you need to do, but you will fall somewhere on this chart. There are those of you who, I know there's people here from the cloud providers, you would be on the far right of the slide. You are very, very good at doing everything in an automated fashion, using very smart and technical tools. Then there are people who, they still have their servers named Minas Tirith, and everything is hard-coded, printed out, and stuck on the wall. So you will fall somewhere in these. So the more legacy operations where you quote you quote IP addresses into your mobile phone numbers. The more modern where you have some form of framework, possibly a vendor framework, which means that you get then locked to that particular vendor, or a true DevOps model. But we can't get there in one day. So I can't convince you, yes, you should do everything automated. We should have a software development framework, and there is no one size fits all. This is a genuine choose your own adventure. So let's start with some goals. Who here has a GitHub account? Okay, let's inverse that. Who doesn't have a GitHub account? Okay, a few brave salespeople. Yep, good one. Build a lab environment, automate your configuration, and then get into the bonus rounds, right? Automate how you track and manage and allocate IP addresses and VLANs. Maybe you shouldn't be allocating AS numbers. Validate changes in your network, and then build a workflow to manage all the things. There are a number of different things out there. These are not all genuine logos of products. I have added a few. So that's you can have a little guessing game amongst yourselves and try to work out which of these are not real products. But there's a lot of different open source tools that you can use. And that's why it's so difficult. You might start off, I am going to use Netbox. You get down the path and all your mates are like, nah, man, Autobot. And then you go, okay, I'm not cool. And then you change over to Autobot and suddenly everyone respects you more. But you have to work out what's right for you. And there's a lot of that, right? There was a presentation earlier today. I'm not making fun of that person, but they talked about one particular way of building virtual labs. I'm going to talk about several others. I'm also going to explain why you might choose different things. And then it's up to you. So testing outcomes, they do vary. We should all start testing on containers. If you're not testing on containers, you better have a damn good reason. But containers give you a really lightweight way to get most of what you need to do up and running. If you want to test how to do software upgrades, who wants to test how to do software upgrades? Well, you should all put your hand up. But yeah, like software upgrades, containers, that concept, that they don't mix. They're oil and water. So if you want to do software testing on zero-touch provisioning or for software upgrades, you are going to need a virtual lab, not a container-based lab, so VMs, not containers. And then if you want to do scale and performance style testing, you are going to need to have a physical lab. There was, again, I'm not taking a complete dig, but there was a talk of hybrid labs, mixing physical and virtual. Please don't. I'll explain why. Oh, no, firm press. There we go. If you look at what you need to get containers, you can do this in a single VM. If you want to do with virtual machines, you can use it in a single VM using a nested VM structure. So you only need one VM and then you run VMs inside VMs, very Inception, but you're going to require more memory and more storage. So if you have a server at home with half a terabyte of RAM, then good on you, let's do VMs. If you have a laptop or an old server that you're making the use of, then containers is going to get you there. Good luck getting physical equipment for testing. the lead times being what they are. Physical is important and you will need to do it, but your physical resources are going to be prioritized towards the most important tasks. So for most of what you need to do, you don't need to do physical. And you also have to think about space, power, cooling, etc. for that. Okay, so how do we move to a software workflow in quote unquote 30 minutes? This is the hardest part of doing any networking lab. You sit there and you go, cool, I'm going to build a lab. It's really simple. I downloaded the image from the vendor, or vendors. You don't have to go with one. I'm going to spin that up, and then you go, oh crap, am I running the right version of VMware or Fusion, or am I going to install it on a VM running CentOS, or maybe I'm going to use Red Hat, or crap, is it 18.04 or 20.04 that I should be running? Which one is the LTS version? Okay, then I have to go download that, and you get, oh crap, that package isn't on that particular one, and you start getting in this cycle that you spend more time trying to get the lab started than actually doing the lab. Who's familiar with that kind of problem? Yeah, it's why we don't do it, because it sucks. And then we go, oh, I'll test it some other day. And all of these problems and being able to do it in a repeatable fashion, that's what slows us down. Good friend of mine, when I was at Juniper, he was at Juniper too. He was also at Cloud Scaling when he used to yell at me, and then he decided he would join us. But pets versus cattle, Randy Bias, right? We treat labs still like they're pets. We build a lab and we want to keep it alive forever, and we want to make sure that our lab environment is well documented, and we're very proud of our labs, and we show our friends our labs, and look, this one has EVPN, right? No. Treat your labs like cattle. Once you finish with your lab, delete it. And you'll be saying, wait a second, no, it took me time to create that lab. No, delete it. That's why I'm not for hybrid physical virtual labs. If you've got enough time to take your virtual lab and connect it to the physical world, you've already wasted your time. You don't need to move cables to do testing. Sometimes you hit issues like, oh, yep, Apple decided to change the silicon inside of all of our laptops. And suddenly all of those virtual machines don't work on some people's laptops. So you have to start from scratch. And in fact, you end up starting from scratch multiple times because you hit one of those issues and then you go, how do I solve this problem? Again, the easiest way to solve the problem is to delete it. Sorry. That's all right. Cool. Yeah, so you just delete it. What are we trying to do here? This is the lesson of why we're doing labs in a slightly different fashion. If we learn these techniques and how we do this in the lab environment, we will start to apply it to how we do it in the production environment. So we don't have to start with the heavy lifting in the real world. We start with the heavy lifting in the virtual world. We adopt best practices there, and suddenly we work out what toolchain works for us. Then when it comes to thinking about how do I transform my physical network into a fully automated end-to-end Cloud Titan, then we know what we're doing. So the key points here is treating your infrastructure as code. Codifying the lab helps you work out how to codify the network. Having a source of truth. Here it's going to be GitHub or GitLabs if your security people tell you so. We're going to focus on how do we do unit testing, which means you aren't running test plans, sending pings on an interface and then writing down what happened. The network should do the testing by itself, and then configuration patterns. The point of a lab is not to learn how to write CLI. The purpose of a lab is to work out if you've written the CLI in the correct way. If you haven't, you'll fix it, and then it will test itself again. Okay, so multipass. Who has heard of multipass? Few people. Good. But then that makes me feel happy because multipass is like my favorite thing of the last 12 months. Multipass is a way that you can take all of that complexity around getting that first VM created, fully automated. You install multipass, go to their website, and then you just go multipass launch name NZNOG 22, and it will set up a VM for you. You don't have to worry about where you're getting the image from. You don't have to worry about allocating all of the different functions to it. If you want to allocate it 10 CPUs and 128 gig of RAM, why not? You can do that. It will get the virtual environment configured for you. Multipass list shows you what images you have. Multipass shell, and then the VM name, and suddenly you're logged into it. Right? Really, really simple. And my favorite command of all, multipass, copy files, file name, and the VM name, and it will drop it into the home directory on that VM. No working out how to turn on SSH or SCP and getting the username set up. It's getting more and more complicated because you also have to have the, these days these are key-based encryption. So you want to have to get, how do I set that up on the host and then make sure that the key is right and then use that? No. You can just literally drop files into the VMs. And this is what it looks like. Multipass launch, name NZNOG 22. It's launched, list, it's there. First time you do it, it will download the software. The second time you do it, it takes about 30 seconds. So the second time you build a lab, because you're going to do it multiple times, because you're going to delete your old ones, super fast. All right, so how do I log into it? And this is small, but you can, when you go back to work after this, you can have a look. What you can see, all you do, multipass shell, and you're in. Easy. So we have to set up the environment, and here I'm going to give you a list of instructions to set up your environment because I do want this to be something that you could actually go back home and try out. You can see this is everything you need to do to talk about what I'm going to do in the future. So if you want to set up the environment, this is what you'll need. However, you can actually codify this into YAML, and then when you instantiate a multipass instance, you can just reference the YAML file. So the second time you do it, you don't even need to upgrade all the packages. It will do that for you. Cool, huh? So every time I create a VM, it's going to have all of the applications up to date, and I can go straight into labs. This has already saved you 3 hours. So let's talk about different platforms. EVNG. EVNG is great. If you've never used it, give it a go. There's a community version. It's free. You drop and drag and create some topologies. You download the different images. You can use Linux images. You can use vendor images. There's little icons that you can create, and you drop and drag and create the links between them. You move them around, make things pretty, and you have your lab. Or, you know which one I'm going to lean towards. The guys at Nokia, they split out into their own thing, but Container Lab. There's a single command you type, and the environment is configured. Easy. So once you have Container Lab installed, you are going to be using containers, obviously. If you use EVNG, that's for the VMs. They also have a premium version that you can buy, which lets you do the container-based lab environments. But if you're going to use containers today, Container Lab is probably an easy way to get up and running. Because once you do that, you can then import your images, and then you just go into Docker, and you say import that file, and now that operating system image is now available for you to use in any of your lab environments. Again, this is dead simple. Easier than on EVNG. So how do we get started? Well, then you need an actual lab. So because I work for Arista, I'm going to show you the Arista one. You type in this command. Again, very, very simple. And you can see a couple of lines of commands. It downloads some standard labs that already exist, and you're away. avd.sh, if you do want the documentation, it is a website. It's also a bit of a joke on the old script files. But you can see there's documentation, there's base code, and you download those collections. You can download the collections directly through Ansible Galaxy as well, if you know what that means. And there's support for a number of different topologies and lab environments. Again, the whole goal is not to test whether or not you can write CLI. It's to get up and running and get testing done quickly. So once you download, if we go back, yes, I worked it out. So if you download this particular lab environment for CEOS, when you run that particular topology file through Container Labs, here you can see it spins up a bunch of images, 4 hosts and a backbone, configured, deployed. So now you have, was it 12 node environment up and running in a matter of seconds. And that's it. You've actually got your lab environment. Now you can do whatever testing you want. You didn't have to spend a lot of time trying to work that out. You can do what your actual job is as opposed to spending the entire day getting your virtual lab up and running. And when you can see how easy it is, you can remember, you can delete this, because it takes you like 5 or 6 commands to set this environment up again. Why would you hold on to it? Now that topology file is where the magic happens. It identifies all of the different devices, the administration IP addresses, the links between the different devices. You could pull that out of something like an IPAM as well, but that topology file is the heart of your lab. If you want to visualize it, Container Labs has a command line. You type in that command and you can see what the topology is. Dead simple. So now you have self-documenting labs. The lab itself will show you what the topology is, as opposed to you putting into Visio what you think it's going to be, and then dropping and dragging and connecting and allocating IP addresses yourself. Let the lab tell you what it is, not the other way around. But of course, everyone's lab's special. And how do you describe your unique lab? Well, what you use is you use GitLab or GitHub, and that topology file, you store that in a place that you can modify over time and that people in your organization can access. And then when you run the lab, instead of downloading, in the Arista example, you download your particular example for the testing that you want to do. I like the GIF, so I was just going to leave that up for a second. Okay, so now we're there. This is the starting point for getting into real conversations around more important things. If we spend all day saying, well, this is how you get a virtual machine installed, this is how we connect a virtual machine to a lab environment, then we're missing out on the actual work we need to do. So in a future presentation, I'd love to come back and talk about some of these things in the bottom row, things like Batfish and PyTest. How do you set up a test plan so when that virtual environment is created automatically and you apply the configuration using Ansible playbooks, that it automatically runs your test plan and your test plan is completed. So you spin up the environment, load the configurations, run the test plans, and your work is done. That's how we get our time back. So we've got PyTest, we've got Batfish, and other measures that will help us complete those tests in a fully automated fashion. There are other aspects here as well around documentation and self-analysis. So if you use the Arista AVDs that I mentioned, one of the neat parts of that is when you run the playbook, it also creates markdown files with the exact services that are configured on each device, not the configuration, but it's like, here's the BGP neighbors, here's the protocols that are turned on, here's all of the services. So you don't have to write documentation about your as-built environment. The tools will create the as-built documentation for you. And then you can host those files somewhere that your ops team can look at those and understand where we go. The final point that I would make is, if you look at where we're trying to go, this is a precursor to probably the most exciting part of what you can do if you can spin up and delete lab environments, which is then you can start getting into using a fully documented lab environment for change testing. So you have, you're going to do a complex change, you've already created your change files, and then everyone rocks up at 2 a.m. on a Sunday and finds out if it works. Or you export the topology file that matches your actual network and the configurations that match your actual devices. You spin up a lab environment. Maybe you do it in a cloud provider's environment because you need more space and more memory. Then you take the changes that you're going to apply on the weekend and you automatically apply that to that test environment and you verify that everything is still working. Now that's the goal, right? To be able to actually pre-test your network changes in an identical environment before you actually do it in the real environment. But to do that, you have to be able to delete your labs. So if you can set it up quickly, run your tests quickly, you can delete it quickly, they become cattle, it becomes more productive for you, and you can start to do things that you wouldn't be able to do otherwise. Cool. I think I do have time for questions, but that's all I had.
Any questions for Rich?
Do you have any wisdom to share on applying some of this to a brownfields environment?
Around the what environment?
To a brownfields environment? Because that sentence,
Yeah,
just export the
great
topology
question.
of your production network, is a lot easier to say than do.
100%. 100%. It is the hardest thing, right? That's why when you go back to, I should have put that much closer to the end of the presentation. We'll get that there. Yeah. So this is, you're going to be on the spectrum, right? And most people, to be honest, we're going to be in the legacy operations space. This is the sort of environment where you're probably doing rancid backups of your configuration once a day. When things go wrong, you manually download a file and try to manually compare it. There's a bunch of legacy features that were turned on because someone who's left your organization turned them on. And you don't know why that was. The documentation doesn't match. I did an audit for an Indian mobile carrier, and there was something in the order of 1,000 interfaces in their network that had the wrong description. They actually said, I point to this router on this port, and it was completely wrong, right? Those are the sorts of challenges we absolutely get to. So the most important part of all of this is getting to reusable patterns, so moving from anti-pattern to pattern, and using self-documenting techniques. So instead of saying, okay, this is the hypothetical of what it should look like, having your actual network configurations be analyzed and create the documentation of what is actually running. So the tools that I showed at the end for the lab environment, self-documenting your lab environment, you can actually use those to show you what your as-built environment is. Once you start getting used to doing that and seeing what is configured, all of your existing manual documentation, you can delete. because it's never going to keep up with what's actually happening. So that's, I think, the first step is moving away from humans creating documentation that the network is supposed to represent, moving towards networks that self-document, and that can be done even in a brownfield environment. The second part is starting to get to templates that you can use for different things. The hardest part of that is obviously, I'm going to assume most people in the room are engineers. Who's a product manager inside a carrier? Good. Because they will want every single feature under the sun, and they want to turn them all on at the exact same time, and they get away from the fact that you need to have pattern-based solutions, right? If you look at where the cloud companies are very successful, and largely because they do this for their own internal audiences, but I think one example I would use is, say, Amazon. You don't order what the knobs that you're turning on. You order constructs, and then the environment will configure itself. And the more we can get product owners to think about that, where they're not selling, I literally had this conversation today, going to a product manager to change a product definition so that the customer can't request whether or not a 1 gig interface is auto negotiation or forced. But you still provide that option to your customers where they can say, I want to choose whether or not I'm doing auto negotiation. The problem is that means that product then defines what you have to do in the network, and it means that you lose that ability to move forward and to create solutions. So yeah, lock your product managers up. Don't let them specify every single aspect of the solution. Work with your customers so that they understand that the solutions are still going to work, and get towards a point where you can start to retire legacy features out of your network. It is really hard though, really hard. If there's no other questions, who actually thinks this is something that they might try out in the lab at home, get multipass running? If you do, this is a shout out for Nokia. You do have access to their software, the SR Linux images. That is in the public domain. If you are an Arista customer, you can download CEOS, which is what I showed in my examples, for free. There is no cost associated. If you're not an Arista customer, talk to us. We'll work out how we can find a way to get that to you. And then you can start playing it. It's not about a single vendor. It's not about using Arista or Nokia. It's about being able to play with this in your own time, in your own space. Once you get your mind around that, then you'll actually be able to take some of these things to production. Cool.
Thank you very much, Rich. I'd like to congratulate you all. We had no phone interruptions in that. Let's see if we can keep that up for the rest of the session. Okay, now we've got Aaron from IAA talking about NZIX. That's right? Yep. Yeah. Cool.
Hello everyone, my name's Aaron and I am here to give you an update on New Zealand Internet Exchange. And where is the green button? Right, so who am I? I do peering things. I'm based over the ditch in Sydney and I work for IAA, the Internet Association of Australia. We do the peering for IX Australia as well as the tech for New Zealand Internet Exchange. I've been at IAA now for 2 years. Quit my job just a little bit over 2 years ago. Something happened just a little bit over 2 years ago. It's probably not the best time to quit jobs, but it happened. What a better time to switch jobs than start of a pandemic. I'm also extremely jealous of you Kiwis. With Chorus. Hyperfiber, are you serious? Like 8 gig residential? Thank you. Don't rub it in. Like seriously, big providers in Australia struggle to get 100 gig NNIs from the non-broadband network, sorry, NBN. So yeah, like you guys got it good. Right, so let's jump to the update with a brief overview of our setup. So our core, quite basic, just OSPF MPLS with VPLS. And we use RSVP with traffic engineering, keep things nice and even. Our hardware is Extreme Networks, primarily our 870 platform, which is a 32 port by 100 gig switch, and we have some older 670 G2s, which are 48 port and 40 gig ports. Our optic vendor is Flex Optics. I primarily love them the most because of the lollies that they give in their packages. But they're also extremely reliable, like really reliable. In Australia, we have many hundreds optics in operation now, and their failure rate is non-existent. So I'm not getting paid by them, just actually recommend them. Yeah, fibre carriers are here in NZ, Vodafone, Vector, and Chorus, all dark. Route servers, Dell's R640s, running Bird 2.07, fully automated at the moment with RPKI compliant, and right now we're dropping invalids. Oh. Out of band network is just open gears, quite simple, just /31s from insert provider here. And security on our IX is just done by layer 2 ingress filtering, plus a bunch of other things, as well as static MAC provisioning. So automation is currently disabled at the moment. There's a few things going on in the background there, but I'll talk about that later. So here's a high-level overview of our ring in the CBD. We have 4 cores going between 220 Queen to MDR. What's the pointer on this one? Yeah, who cares? Yeah, they're just standard 100 gig LR4s, nothing fancy. Both have single dark fiber to data vault as well. We use circulators on that to get like duplex on 100 gig. Circulators are pretty cool, but just being mindful, you want to be careful of reflections. Expect fiber breaks. Factor in the optic that you're using if it's going to break, because you're going to get reflections back. Now from VDC Albany on the bottom right, that's our long paths back to the CBD. So they're about 25 kilometers. They're just 100 gig LR4s over 4 cores each path, which give us 200 gig per path across the Harbour Bridge back into the CBD. So that's what we've been currently running for 2 years-ish. And with that, we've been doing a lot of traffic, quite a lot, yeah. So continuing on from the last NZX update in 2020, from the bottom left is Jan 2020. We're peaking around 100 to 140 gig per second per day. This is just Auckland Exchange. Now we're going to crazy amounts, like really pushing traffic to 390 gig per second. So really starting to move some bits. Looking at port growth, 100 gig has actually been a great success. It might be a bit hard to see here. Oh, it's not too bad. There's the COVID line down the middle. Yeah, 100 gig ports have been going up quite a bit. 10 gigs, they do a little bit of dips when everyone moves to 100 gig, which is great. 100 gig ports have been dropping off. And we're now at 20 100 gig ports. Actually, as of today, 22 100 gig ports, but we're under NDA, so I can't talk about that one, but you may know who it is. Just a few more exchange bits. So total route count has doubled since 2020, from 50K V4 to like over 115 now. 25K V6 to around 50-something K now. We've introduced new looking glass a while ago. Alice looking glass, it's quite a good looking glass. It sort of hooks into Bird quite nicely and gives you a valid reason for why it's been filtered. So I do highly recommend, if you guys are bored, go to that website, lg.ix.nz, see if anyone's filtered and point the finger at them. Send us an email if you need us to have a look and fix anything up. We build peer policies off AS sets, so we do route sets as well in the background, but it's primarily AS sets. So build an AS set. If you're not sure how, there's a link with AppNic. Thanks, AppNic. Yeah, quite easy to set up. Their route servers are automated, so they get refreshed daily. So route server 1 is at 2 p.m. and route server 2 is at 3 p.m. So if you make an AS set change, yeah, that's when it's going to actually flow through. So moving on to Christchurch, it's been pretty good growth. You know, it's a little bit smaller than IX, but it's getting there. We've got 15 10 gig members and a 140 gig member. Big traffic, about 7 gig, V4, 1.3K, and V6, about 250. We have a new Chorus Edge Connect coming in, so if you have a Chorus handover port, yeah, you should be able to connect via that in maybe 8 weeks or so for now. We'll see what the lead time is. In terms of content, as the courtesy of Vocus, they provide Netflix over Christchurch. 5 Fastly just turned up their new ports. They'll be live soon. I think they got 2 10 gigs. And our beloved CDN Cloudflare may finally connect soon, but we'll see. And to the Wellington Exchange, the new baby. It's seen pretty good growth. It's only 6 months old now. 1 year free period, so if anyone wants to join, free port. Port growth has been quite good. We have about 13 10 gig ports, and we got 100 gig port, thanks to Devoli. Where is he? Somewhere. Yeah, peak traffic's going good. Yeah, 5 gig per second peak, and route count 1.4, 1.2 K V4, and around 250 V6. We're in Spark DC Wellington, aka Featherston, and we're also in Extreme DC, which Dion is here somewhere. There he is, waving in the back. He's the operator of the DC. So the sites are just connected through Chorus Dark, nothing fancy. North and east, northeast and southwest routes coming out of Spark, which has been going pretty good. And that's really it for just the update side of things. We also have a little bit of future going on with Auckland Exchange, and I'll go into that. Quick disclaimer though, any future stuff I talk about is only a draft. It's not approved. But I'm basically asking for a bunch of money from Dave Mill, and he's a little uneasy about the amount of I'm spending. Need it to do the things, of course. As you can see, Dave there hugging his beloved piggy bank. he's got a little bit more hair there. Maybe a bit more junk in the trunk. So this is really just an overview of the proposed 1 to 2 year plan. It's a little bit dense, so I'll try not to go too slow with it. But new POP, Datacom Orbit Drive, that's where we're looking to build to first. And hopefully with it, we'll get to CDC as well, Hobsonville or Silverdale. But primarily, we're looking to incorporate Datacom into the ring to start off with. It's going to be re-architecture of the ring. We have some overlapping fibers. We got it's not directly overlapping, but they're quite close. For comfort. So we have some in the CBD. They both go over the harbour bridge. This is to go from CBD to the northern end, Albany. Yeah, it's a little bit of overlapping, and there's a bit of overlapping in Albany, which is a bit ugly. So to solve that, we're building out to a new western path. So from the CBD going up, it's about 35 kilometres. And on that path, we're looking to do 400 gig DWDM with muxponders. So these are utilising smart optics DCP 404s with 400 gig, that's a mouthful, QSFP DD 400 gig OpenZR Plus with CMS application code 6. Yes. I'm actually looking for third-party optics, so if anyone knows anyone, let me know. My ETA for some people are about August, and I'm curious, because they're quite hard to find. Part of this is a bunch of new switches, 100 gig switches in each site, give it a bit more redundancy so we can do outages a bit easier for firmware upgrades. And the end goal is really a 400 gig redundant, diverse network to massively reduce single points of failure, because no one likes that. So let's have a look at the KMZ overview, or not, because I'm not sure if you guys saw this, but there was a France situation where all the fibers were severed. It was coordinated sabotage. Someone went around and chopped it all up. That's not nice. And so I'm not going to give KMZs out. You're not going to see the exact fiber in the ground, but I'm going to do some crayons and some higher level overview so you can use your imagination. Yeah. So here's my very accurate map of our current KMZ fibers. CBD down the bottom, MDR and 220, diverse-ish paths. As you can see, there's quite a bit of touch and goes, that little thing in the middle there, and up at the top in Albany is just a bit weird routing paths, to be honest. Yeah, so that's our current setup, and this will be what we're looking at for our updated sort of plan. Red path is that big western path I'm talking about. It's about 35 Ks. That's where we're going to put DWDM muxponders. We're going to need amplification for that. 2 cores, 400 gig, perfect. That should give us a lot of redundancy for traffic. So going from MDR and the CBD, Western Path up to VDC Albany, we'll have diverse across to Orbit Drive, Datacom, and then back down on the Eastern Path back to the CBD. That's going to be DWDM. Shouldn't require amplification on that. And then from 220 Queen back to MDR, there'll be diversity there as well, physical diversity. So this is just a, I guess, higher level overview of what that looks like compared to previously. Main bits here is it's 400 gig all the way around, and we're just, to reduce our OPEX and keep Dave happy, we're going to be using circulators where we can. So 4 cores, 400 gig, and DWDM on the Eastern Western Path, of course. And that's pretty much it for the update. This is looking to the far future, build a new portal. That should, we built a new portal in Australia for IAA, and that should come to NZIX as well. We'll be utilising Ansible automation, and some core changes we're looking to go through. Oh, there's a little comma there after 400. What's after that? I don't know. And Spark is joining. No, they're not. But look, we're here with open arms and more than welcome to join. And that's it. Thanks. Any questions? If I can't field them, I will pass them on.
Looks like you're off the hook. Oh, yes. Thank you.
I'm 27 years old. That was my first public speech, so thanks.
Now I believe we have Chris from NZIX talking about things that NZIX might do that aren't exchanges. Okay?
Ooh, there's 2 clickers. All right. As Richard introduced me, Chris Browning. Day job is Lightwire, ISP in New Zealand. And because I apparently like to work harder, I also help out with the NZIX and have the role of chairman at the moment. So first off, what is NZIX, in case you don't know? Predominantly, we're known for running internet exchanges in New Zealand. Auckland IX, Wellington IX, Christchurch IX. Hopefully you guys are all pairing with them. It's what everyone thinks we do. We're member managed. We are owned by the members, or sorry, the people who pair on the IXs are our members. So the people using the IX are, the members are for us. And we're a not-for-profit. It's only one little thing, and our treasurer doesn't like showing this, but that is a true graph of our bank balance over time for the last 18 months. And as you can see, for a not-for-profit, it's actually growing at a reasonable, steady rate. There's some dips, and if Aaron gets his way, there's going to be another big dip shortly. But, it is growing on this trajectory. And that kind of led us, before I get there, the thing is we're actually more than just exchanges. Like, we were known for the IXs and exchanges, but it turns out we actually came from our Australian cousins who started us. So IAA started out, it was WAIA. They founded us. They actually put up the initial cash, got some people interested in doing this stuff. And because of that, our society rules are actually roughly based on their rules, or what their constitution was at the time. In Australia, unlike New Zealand, they don't have an Internet NZ or an Internet Australia. So IAA actually forms some different functions over there than just exchanges. They do some industry training. They do some industry news and blogs. They do internet advocacy, which, obviously Internet New Zealand does a lot of in New Zealand. And they do some really basic interpretations and guidance, and they're looking to do some more of that over time. We kind of have groups in New Zealand doing that, so we don't need to. So what else can we do? yeah, what does our rules actually say? So we sort of have rules that says support, protect the interests of the internet community, assist the operation and expansion of internet exchanges, promote education and informed decisions in matters relating to the internet. This is at the top of our rules. It also says, I must have gone through 2 slides there. Yes. So this is the very top. We are to establish and maintain and extend interests of professional internet community throughout New Zealand, underlying principles of society to widely promote the internet, its applications, and associated technologies, also advancing internet services, benefits, private citizens of the community. So, oh, I see what's going on there. Now I make sense. All right. So there's a few things, but our rules do also say later on, much later on, that we are to establish, operate, and administer exchanges. Again, we are doing what we're supposed to do as well. But it's interesting that we've got these other bits to what we're about, which is kind of why we're talking about this stuff. So in the NZNOG AGM last year, about June, we had the AGM, and I actually set out a challenge. I said to our membership who turned up, it was great for people who had drinks with us, we are making profit. We're not allowed to make a profit. We should probably have a plan for what we're going to do about this. So I just raised the challenge out to the people there. And I'll be honest, there was quite a few ideas thrown around the AGM. It was a good discussion, thanks to those who were there. Some sank immediately. They weren't great ideas. Some sank later when we had a look into them. Sounded like good ideas, they weren't. But one in particular really stood out for us to look out further. And that's kind of, oh yeah, there's the thing, we want to talk about it with the wider community before we dive into it. So that's kind of around network engineers issues in New Zealand. I don't know if you've looked around the room today, and obviously you all know each other, and you probably knew each other 10 years ago. Turns out we're all kind of getting a little bit older now. And the incoming skills, we're told, is coming in lower. The people who are coming in to do these roles in the future, they're not got the skills we expect. They aren't being taught them at school, they're not being taught them at university or tech. They don't have the skills we want. Lacking gender diversity, again, look around this room. But the big one as well is, it used to be, if you talk around this room, if you talk to people, get to know the people who built industry in New Zealand, you'll talk about how they broke ParadiseNet, how they broke MaxNet, whatever residential ISP they cut their teeth in, how they broke it and how they learned. This is, you know, the history was how they broke it. I mean, I broke Rural Link, and I broke wireless. That's how we learned. But no more, like everyone's working from home. We're not allowed to do this. So how we learn isn't how the next generation's going to be able to do it. The other thing is, and this is a little more hidden, there's so much more automation. All the juniors get to see is the output of the automation to some ISPs these days. They don't get their hands dirty. They don't have that raw thing. It's the same thing with airline pilots, you know? All they do is sit in the end, the plane flies themselves, and then suddenly do they know how to fly it when they have to? Obviously, they put lots of things in place to help with that, but again, the problem is arriving in this industry. I'm kind of putting this one on italics and kind of ignoring it. Some of you guys, you know who you are, you're holding on to your jobs and you don't actually want those new guys to come take them yet. So I'm just ignoring that, doesn't help my slide deck at all. So what can NZIX do? This is kind of the question that we're looking at. We're kind of in a unique position. NZIX is known to be quite neutral, very neutral. Our membership's very wide and diverse, and our membership are who govern us. We're a Chorus customer, and we're onboarded for NGA services. Why? We need a DFAS, but turns out when you get onboarded for NGA services, you get onboarded for them all. Chorus tail extensions exist, and you can long haul to pretty much anywhere in New Zealand that's the Chorus network is. We have a relationship with ISPs. Well, I think we have a relationship with ISPs. We have relationships with clouds. We have relationship with some IXs for some reason. And we also have relationships with some data centers where we can put some stuff. So we're kind of in this relatively unique spot. So what's the sort of the idea that came out of this is, could we do a form of educational ISP? The idea would be use our relationships to get free or cheap transit. We've had offers of 5 gigabits connectivity for some people, and you know, I think we got offered up to about 8 gig in total. We know IXs are friendly to us. And the idea is, can we enable learners to get chorus connections to an NZIX lab at cost? Thinking second port on an existing ONT sort of stuff to get people into a lab. But we also have to think carefully about how we'd run this, because we also don't want to be in a position where we just create this cheap ISP, start undercutting our membership, and our members get grumpy with us, because we don't want to be doing that either. So we might do something, ideas around that is like members have to sponsor you to get on or something, but there's also lots of ideas around how this could work. We also, work with various vendors who might be able to provide switches, routers, BNGs, potentially virtualized, potentially physical. Provide containers for AAA and other things. It takes more than to run an ISP than just a couple of routers. So free radius, potentially look at LI, how that might fit in. But basically provide an environment where you can be shown a national New Zealand network working, and be a customer of this network, go in there, change it, figure out how it works, break it, fix it, hopefully, but learn. There's a few different things that you can do with it. You could try out new technologies that you're too scared to try in production. EVPN, segment routing, QoS, I don't know, different people, different things. But, you probably aren't going to try some of these things in your own environment. An environment you can try it or learn about them. So the target audience for this sort of concept is obviously members who want to try out features with a vendor. The vendor's like, hey, we've got this feature, come try it out. Provide a pre-built lab, looks like New Zealand, how you might do it. Want to test upgrade paths. We had people before talking about labs test upgrade paths. This is sort of the same sort of idea, but we help out with the setup. Replicate bugs and troubleshooting in a non-production environment. But here's where it gets really interesting. If you've got members in your call centers or junior NOC engineers who want to figure out how the stuff works, want to spend time, you can put them in an environment where they're not going to go insert things into places and drop everyone offline. A safe environment. The other thing is, if you just want to try out a vendor, maybe you've been using vendor A for the last 5 years, but you want to know how vendor B does stuff. I'm not going to put vendors' names in there, but if we can get vendors on board, multi-vendor, you can try this stuff out. The other interesting thing is, what if vendors want to provide pre-built labs built the way they would? So how they would set up BNGs for IPOE or PPPoE, or how they would set up segment routing for, a New Zealand-shaped network. That sort of stuff. And potentially, could we provide some environments that potentially go into universities so that rather than us having to, okay, there's a lab, but we now have to train people still, that's still a drain on our time, could we provide the lab and some guidance to universities to potentially use them, or other tertiary environments, or potentially schools? There's been suggestions that schools could be interested as well. Way down the track, there's a lot of work to get a curriculum going. Yeah, so basically, could we create some form of assisted curriculum to help train people? So there's some crazy ideas. The whole point of this talk is to sow some ideas and solicit some feedback from you guys. So where are we at the moment? What have we actually done towards this? So we've engaged with some potential bandwidth buyers. I've kind of hinted before, we found some. We have success on paper. We haven't actually, tried to make it work. We've just got some people saying, yeah, they will. But these things that don't always work out. We have engaged with a few small subset of vendors. We've been basically working with the vendors that we have easy access to and relationships with. But pretty much all are keen to participate with the price of their logo on whatever website we put in. A lot of the value for them, they see it as if they're getting the next generation of potential engineers learning on their kit, they're getting a leg up. So they're keen to help out. They're all pretty much keen to provide whatever software. So if they got virtualized, pretty much they'll all go, yeah, we'll give you virtualized instances of our things. Some of them, like, they're already available, so just grab them. Some of them would consider, in principle, potentially either free or heavily discounted licenses if we could find hardware from people who didn't want it anymore to put in the network and make it keep going. Sort of waive some of that tape. We've also heard mutter maybe hardware, but honestly, in this current environment, I don't think we're going to get anyone giving us any hardware that they could put in the network or sell to someone. But they've also indicated some level of openness to their various tacks, building a couple of deployment models of how they would build this network to show people. So what are we actually looking for? Well, really, like, there's a lot of ideas. There's, you know, various different conflicting things about how, you know, we don't upset our membership by building an ISP. There are ideas about we should actually open it up a little bit to the public because having some real users on it makes it more real to learn on. Again, how do we do that without upsetting them? There's also a little moral thing that keeps, you got two guys on your shoulders. If we, provide access to the community that can't afford the internet and then experiment on them, there's something that sort of goes, maybe not. But honestly, we want to know if this is something that this industry are interested in. Is it something that you would use? Let us know, either for yourself or for your juniors or just available in the organization. If it interests you at all, just please let us know, because if we do go down this route, it is a lot of time and it is some money that we could be using on something else. So please let us know, and in particular, what parts are interesting. The various different things I've talked about, which is the bit most interesting to you guys. Do you have thoughts and ideas that would actually contribute to this or shape this? Also, do you have something sitting around collecting dust that might be better off in a lab like this if we built it? So come find us. I know I've been slotted right at the end of the NOG. I'd have loved to do this at the start where we had all the different things, but please do come find us. I will go out to the stand at the very end for a little while, so if people can come find me. But honestly, there's a few committees around. Dave's been up on stage a lot, myself. You saw Simon present earlier. You probably know one of us, so do chat. The other thing is, we all hang out on the NZNOG Slack. You can find us all there. If you're interested in any way or have ideas, reach out. But I will also, if time permits, take any questions that people might have.
You've got a couple of minutes.
Nothing.
Oh, one.
Kia ora. First of all, I think this is a great idea. I think that for it to be a success, the success has to be in its simplicity. I mean, there's a lot of really good things there. I am really kind of keen to help get students in. Something that you might want to consider is that you allow anyone who wants to connect, and you literally just put a 7 p.m. curfew on it, and at 7 p.m. the international transit stops. Because then you're not prohibiting people from being able to connect, you're not necessarily disrupting existing members' revenue streams, you're just not letting people use this as a production environment because it doesn't happen after 7 p.m. Nobody wants to stop watching Netflix at 6:59.
Yep, interesting idea.
But yeah, cheers.
Yeah, definitely. Definitely echo that point. To be careful not to actually become a proper ISP or be, taken advantage of. But also with, as you said earlier, is not allowing just everyone that wants cheap internet, that can't afford proper internet, to hop on board and wreck the internet. Whether there's some kind of eligibility criteria or something there, and also how, obviously you need to cover costs, as you said, how the billing side works, whether it gets billed through the sponsoring member or whether NZIX is going to end up with a much larger ledger of debtors, have to follow up on an accounts process and all that mess as well. So food for thought.
Yeah.
Yeah, I was just going to say, this seems like a great idea and an excellent way to learn. One other maybe slight comment. Obviously, some of us here are from huge ISPs that have massive budgets and racks full of labs and test equipment. Some of us here are also working for smaller ISPs or bootstrapping a lot of stuff. So maybe there's a potential angle where some of the smaller providers would be interested in like actually labbing stuff themselves. Because, you know, every time you buy like a MX204, it's not cheap. Every time you buy another 10 gig switch, I have 7 in my living room at the moment, they're not cheap. So just food for thought, but maybe like actually a community lab or even a member lab could be a cool idea where some of our smaller providers could like potentially collaborate on some of the stuff we're doing.
Yep, so you're talking about a physical lab somewhere that you can go and visit. Or access, really.
Physical lab or virtual lab or something you can access. That would actually potentially have some value to not just the students, but also maybe some of the other people in this room. If you're, if you're thinking of ideas to spend your sweet cash on.
Yeah, so to be clear, like, it's interesting, like, it was one of my points, right, is this could be useful as a training tool for juniors, or it could be an interesting thing for training tools for yourselves, right? If this was built, I would probably go and deploy, or at least look at a couple other BNG solutions in case, I wanted to change my BNG provider at some point. The other thing I will point out that I didn't say in the chat is a really interesting group of people who have shown interest in this that I did not expect is some of the suit-wearing people in the room. They actually are right behind it as well, and I can only assume that's because I think they see the same thing as a sort of a risk as well of not having people coming through to have the correct skills and security thoughts and whatnot and experiences coming into the networks. Last question. Yep.
So how do you see the balance being between the lab sort of side of things and the service provision side? Because it feels like there's a bit of a tension there.
Yep. So this is details I didn't really go into, but in my head, we would actually ring fence it and you'd have multiple labs going at once. Obviously, for a lot of things, you can do virtualizing containers. We would look at doing that. So you could have a lab, they could have a lab at the same time. We would ring fence it, so you wouldn't be necessarily, you'd be connecting to fake handovers and fake transits and whatnot that was ring fenced by an edge.
Sorry, where I'm sort of coming from there is actually having customers on the network isn't necessary as
No, yeah. So if we were to go down this route, it would be staged. It would start off being something in my head where you, the membership, would use it with your juniors. We wouldn't be providing any training material. And then potentially later, if it keeps being official over time, it's not going to be like, we're going to come up with a finished solution on day one and present it. It's going to be an iterative thing. Yeah. Cool. All right.
Okay. Thank you, Chris. You may have noticed we've had some talkers who've come virtually because of illness. We've had some talkers drop out because of illness. And so we now have a replacement. It's Liam Farr to the rescue again with the lightning talk that grew up. Liam's going to talk about Starlink.
Just bear with me for 1 second. I have a lot of emojis and I don't want to do a brewer, so all right, and I think we're good. Cool. So today I'm talking about Starlink hacks. Hardware is easy. And this is kind of, I guess, my adventure into the world of designing and producing some real-world hardware. And of course, a little bit of information along the way about Daddy Elon's sweet space-based internet. So for those of you who don't know me, and I guess I'm semi-infamous with Simon Allard now, my day job is in corporate IT. I attend a lot of meetings. I work for a large property group, so I'm either in meetings, looking at plans, or wearing a hard hat. And my side hustle is ISPco, where I also have a small ISP that pushes a bit of traffic around the country and has a presence in a few chorus exchanges. I've got 0 previous hardware development experience, and that makes me uniquely qualified for this task. Yeah, so first some background. I should probably look at my notes. So back in September 2020, I brought some land in the rural Hawke's Bay with my partner, Ben, who is in the audience and also features a little bit in this, with the goal of building a house. It's a beautiful site. It had power to the gate. It had 1 megabit DSL to the boundary, which then went back to like a remote little mini exchange and onto a wireless link. It's crap, you don't want it. There was no cell phone coverage and there was no WIS coverage, but lovely site. So of course, you know, new house site, what's the first thing you do? Maybe you engage an architect, you do some plans, you start doing that. No, step 1 is making some Wi-Fi. Now, in this case, about 3 months after we bought the property, and this will actually lead on to the main talk, about 3 months after we bought the property, RCG, set up a cell tower that's just over the horizon from us, maybe like 10K away. So there was some 4G, but it wasn't great. So we built a small solar site, and by we built, I drank the pals and Ben operated the tools. So we built a small solar site to get some basic Wi-Fi at the section. We literally put a MikroTik Chateau zip tied in the box, 12-volt solar, and that was kind of version 1. And then, of course, you know, what's the next thing you install to your section? You know, if you're not building a house, then obviously you install a hypervisor. Also have a hypervisor environment on site. It's a little HP. It runs Proxmox. If you look really closely, you'll see that we assembled that over a weekend from spare parts in a shed, and there is a Fisher & Paykel dishwasher blower fan in there. And we originally had the MikroTik doing temperature control, running a script, and turning the fan off and on. That actually didn't work out so well, so now the fan just stays on. And it screams a little bit now, but it does work. And the virtualization environment was, you know, it runs Proxmox. I've got LibreNMS, some smoke ping, running some CCTV, just general applications. So cool. So step 3 towards maybe actually building houses, you need some power. So we're both poor network hobos, and thus we're doing all of the work ourselves. So that means trenching, diggers, playing with all the cool toys. We're 100% doing it because we're poor, not because we like playing with diggers and power tools and things. So eventually got some power up to the top of the site. Rocks are fun. We got power most of the way up to the top of the site, and then we hit rock. We did eventually get through it. I don't have the photos of me on the jackhammer. I tried that, failed, and then we just hired a bigger digger. But now we've got power at the top of the site, and finally my pre-ordered Starlink had actually turned up. And I'm like, cool, we can finally replace the shitty 4G and the 10 gig limit with Daddy Elon's internet. But of course the problem is we don't want to stick mains all the way up the top of the hill. So I'd really like to power this off low voltage DC, 48 volt telco power, something like that. So off we go to do some research. Research is mainly looking at Facebook and trying to work out what everyone else did. And it turns out there's one guy called Eli, and he worked out how to get PoE Starlink actually working. Now, why this might be a challenge, you're like, well, why can't you just plug it into regular PoE? If you can read the tiny text on the Starlink power supply, the circular dishy power supply supplies up to 180 watts and up to 150 watts up to the dish. So dishy is quite hungry. And if you look below that, I've just quickly Googled PoE power supply standards, and you'll see regular PoE is about 13 watts to the device, PoE Plus is 25 watts, PoE Plus Plus is 51 watts, and then PoE Plus Plus Type 4 is 73 watts. So there isn't a current standard that exists to actually get 150 watts to your dishy. So the first thing I did was watch Eli's video. I was a bit confused, and generally part of my design process when I'm doing anything in engineering is I draw a diagram so I can work out, you know, what the fuck am I doing? So I produced a diagram, And people were using this Tycon converter, so I produced a diagram that showed the Tycon and swapped a few of the pairs around. Why is that important? Well, because Starlink's PO is proprietary, they don't really want you just bringing your own PO injector. So regular 4-pin PO sends the positive current on, positive voltage on pins 1, 2, 4, and 5, and the return back on 3, 6, 7, and 8. Starlink PO, instead of using 1, 2, 4, 5, uses 1, 2, 3, 6, and return on 4, 5, 7, 8. So that means that as soon as you plug your Starlink dish into a regular PO, it just shorts it out and shuts down the PO. So hence, you need to get PO onto the correct pins. So I made the diagram that shows how to swap stuff around. And because sharing is caring, before I'd tested this design in the field, knew really much about it, I posted it back onto Facebook. This will of course come back to haunt me later because this design wasn't tested, it's not the greatest, it has some problems, and now I have the internet arguing with me and posting my own design back to me in their arguments. And of course I didn't watermark this at all, so, or any attribution, so yeah. Yep, you get the point. So proprietary PO, why would you do this? Well, okay, we've actually got 3 generations of Dishy, generation 1, generation 2, depending on how you want to version it, and generation 3. So generation 1 is circular Dishy with the black accents. So it's got the black mount and it's got the black cable. That one's quite hungry, so that one uses maybe 180 watts, but at least 150. Generation 2 Dishy, aka the cat warmer, that one, they kept all of the molds and things and the design the same, but they deleted a few of the phased array antenna elements, so it now taps out at 150 watts. And generation 3 Dishy, the square one, they've further optimized their power design, and now it only uses 100 watts. So it's getting a little bit more sane. So again, proprietary PO, why do this? Well, I think currently Starlink have 250,000 subscribers. They're doing regular-ish hardware iterations. They're pushing out weekly software updates. They have no real customer support. Or they have customer support, but they have customer support for 10,000 customers, not 250,000. End users like to screw with shit they don't understand all of the goddamn time. So when you have a high power system that's 150 watts, you need to ensure standardization of this self-installed CPE. The last thing you want is you roll out a software update, the device requires full power, it can't get it, and then you've bricked 10,000 dishes because you've got idiots installing them in setups that aren't designed to run that way. Or even worse, someone's using a really janky PO injector and then they set fire to their house. You just don't want that liability. So make your PO system proprietary, make your connectors proprietary, which they did in version 3, Square Dishy. Stop people playing with it, makes your life from a customer support perspective way, way easier. So there is method to the madness. There is a reason why they've done this. So, seeing as I produced that diagram, and my diagram used this Tycon power injector, version 0 was let's go shopping to our favorite Wi-Fi vendor, Go Wi-Fi, and brought one of these. Now, I'd sent the diagram to Ben. Ben had said, screw that, I'm going to open up the PO injector, and I'm just going to modify some of the traces so you don't need the janky swapping things in and out. So that's what we did. Version 0 of the PO injector design was just cutting a few traces to get PO on the right pins. And as you can see, soon fire. And pay particular attention to the PO magnetics module and its unique vendor branding. So testing version 0. First, we actually did check that the pinout was correct because you don't want to plug your $1,000 satellite dish with passive PO on like a reasonably high power circuit. You don't want to blow it up, right? So quick test with the multimeter, seems to work, and we installed it in a box in the lab, and hey, it worked. Cool, awesome. Skip to a week later. Who knew? The data sheet lies. So if you look at those 2 transformers there, it's kind of spot the one that doesn't look right. It turns out that the 130 watt max rated Tycon was not actually 130 watt max. In fact, there was no vendor information at all. It's just a generic part from somewhere. So yes, we had this in production for about a week. Starlink did a software update. During the software update, it goes full power, actually sucks 150 watts, does some sky scans, other things, and it smoked out. So yeah, lessons learned, the data sheet lies. So version 0.1 time. So at this point, we're like, well, we blew up one magnetics module, had some air fiber power supplies lying around. Air fibers draw a lot more power, so we're like, cool. Open that up, desolder the air fiber magnetics module, put it back onto the Tycon injector. This one also doesn't have a data sheet, and if you Google it, you'll see that it costs about 80 cents to manufacture. It's used in a lot of PO injector designs that seem to tout themselves as being rated for about 30 watts, so it's definitely not a 150 watt rated thing, but you know, it's in an air fiber power supply. It's got to be better than whatever Tycon shipped without any branding. And that actually did work. So we kind of got proof of concept, cool, we can make this work. So next step for me was like, let's build some hardware. I've never done any circuit design before. I've never done any hardware design before. I kind of flunked out of some electronics engineering courses at AUT. So again, uniquely qualified for this task. It was like, I don't know, about 6 p.m. on a Friday night, and I'd probably been drinking, and I was like, yeah, let's learn CAD. Let's learn KiCad, let's design some circuits. So started by looking at circuits, post circuits from other vendors, grabbed some example circuits from, I think it was Texas Instruments off DigiKey, looking at what they're doing in the designs, started doing circuit board layouts, that sort of thing. I'm not going to post my actual circuit board layouts because last time I did that, someone downloaded them all, sent them to a contract manufacturer, and then tried to rip my design off. So hence, you don't get the actual designs. But it turns out circuit board design is a lot more complex than you think, and then you get into all sorts of weird shit like VARs, which are magic because they have inductance and all sorts of crazy things they do to the signal. But yeah, bashed out a circuit board design in KiCad. I think I started about 6 p.m. on a Friday. By about like 7 a.m. Saturday morning, I had most of it working, and then that got refined over the next couple of weeks. I had a massive amount of help from two of my friends who are both like professional electronics designers. So I didn't do this all myself. I had a lot of help, but you know, I guess the point of the talk is that you can bootstrap it yourself. Cool. So once you've actually designed your circuit, and well, once you've designed what your circuit looks like, then you actually need to lay out your PCB. Auto route, auto layout, as you can see, is magic. You press the button and it spits out something like that. So once you've got your, I guess your circuit design, actually the task of actually laying out all your components on the PCB is like a whole nother piece of work. And there's a bunch of learnings in there about kind of design rules I didn't know of, things that you can and can't do, like in your traces, you don't want to have more than like a 90-degree angle, otherwise when they etch the acid gets stuck and your board looks weird. So again, lots of learnings. Once I'd kind of got something together that looked okay, then I sent it back to my friends. We reviewed it a few times, kind of pushed out multiple iterations and kind of got something that looked like, yeah, hey, maybe this will work. So through the magic of the internet, a month later, we have a circuit board. Some props. And as you see on screen, it does exist in real life. This is kind of the first design prototype. Cool, the internet's magic. You can draw something in CAD and it turns up at your house a month later on the DHL. Even more surprising, holy shit, plugged it in, it actually links up, it links up at a gig, there's no errors, you know, shot, first time, actually worked. Cool. So now some field testing. So next phase of this is to get it into the field, replace our janky Tycon injector. You can kind of see the box in the field that Ben wired up that has everything in there. When we first installed this, plugged it in, it worked, and we're like, yay, the magic smoke didn't come out, it actually works. And then 4 hours later, after Ben had left site, everything went dark. It turns out what had actually happened is, unlike the previous Tycon injector, which didn't have any fusing, he had actually installed a proper fuse in line here, but it was only a 2 amp fuse, and so when Dishy decided to do a software update, and it's pulling 150 watts through a 2 amp fuse, it's not going to work, and we're just blowing the fuse. So, you know, crisis over, 4 amp fuse in there, sweet as. So now the next part of testing was, hey, I actually want to try this on a load bank and see how it performs. So I brought a China load bank off AliExpress. I paid the extra $5 US for the RGB LED version, and as you can see, it's super worth it. That load bank is actually really cool. It's like 60 bucks. It has RGB LEDs. It has like an OLED screen or something. It's got Bluetooth. It's got heaps of functions. And it has a Android app that certainly contains spyware. Through the magic of friends who actually do this professionally, we stole a FLIR from their lab because we wanted to actually get this under a FLIR. And one of the design considerations with the PCB was, hey, we want to design it for a particular temperature rise. So we want to design it so that you only get 10 degrees of temperature rise at full power, so that we don't have too much resistance, we're not making it too hot, and we don't design anything that catches fire. So we got it under the FLIR, and it's actually pretty good. 29 degrees ambient. We're only getting 13C temperature rise on the PoE magnetics. These are actually rated for 150 watts. There's only 2 major manufacturers of this, and they only do kind of small quantities, but PoE Magnetics is making most of the heat. You can kind of see on the left, that's the top-down view of the transformer. The next one's the underside view. And then you can also see even your Ethernet jack with the PoE coming out heats up a little bit. And then, of course, your cable also heats up a little bit because you are shoving 150 watts out of cable. So what did I learn from version 0.03? Objects on screen may appear bigger than in real life. When you're designing this on a 38-inch widescreen and your circuit board is huge, the mounting holes that you think look perfectly fine, as you can see here in reality, may sometimes be too small to get actual real-world screws through them. Other learnings, these things are expensive. The first 5 of these I made, which was like the minimum order quantity, cost $120 US each. And it's probably over-engineered. So 4 CU of copper thickness, so that even the smallest traces would only have 10 C of ambient temperature rise. And actually, the most expensive component is the transformer that costs about $10 US, as opposed to the 80-cent one that everyone else is using because it is rated for 150 watts. Proper TE jacks and like high-spec TE jacks. They make, TE's brought everyone these days, so they have a lot of different product portfolios. And then also a proper telco-style TE power connector, and then high-rated passive components. So decent resistors, decent capacitors, hopefully nothing that will go bang. So yeah, possibly over-engineered. As I'm going along this journey, I'm posting this on Facebook and Twitter and a few other channels, and it turns out people want them. Who knew? So bring on version 1.01. The only thing we changed was to put in bigger holes, and because of the bigger holes, we made a bigger PCB. That's it. So yay, hardware is easy. Also, the price came down because we made 20 units instead of 5. They're now costing $60 US each. So it's becoming a bit, that's cost price, but it's becoming a bit more affordable. So testing version 0.01. Oh shit, what did we fuck up? It's linking down every 1 hour and 55 minutes. So get this into the field, and the Ethernet interface is flapping. Every 1 hour and 55 minutes, pretty much on the dot, it's going up and going down. And you're kind of scratching your head going, well, what could be causing this? Did we screw something up in the hardware design? And of course, the more you stare at it, the more you go, well, that's quite weird. It's happening exactly every 1 hour, 55 minutes. It's probably not a fault with the hardware design. It's probably something else. And you start wondering, like maybe do SpaceX have some sort of heartbeat between their own PoE injector and Dishy? Are they doing a check? What's going on? You're kind of scratching your head here. Also, bear in mind, I live in Auckland. This unit is in the middle of the field in the Royal Hawke's Bay. I can't exactly just, walk out my door and get to it. So this is a little bit of a challenge. What do we screw up? Port flapping every 1 hour, 55 minutes. I'm starting to kind of get like orders, people who want things. It turns out at some point we rebuilt our wireless high site, and we swapped from that MikroTik Chateau router to a MikroTik Hex PoE. And the Hex PoE was actually the cause of this issue. We went and swapped the Hex PoE out. Again, thank you to Ben. I made him go and do this at like 7 p.m. at night in the rain, which was a 2-hour round-trip drive and then a walk up a hill. But we got the Hex PoE swapped out for an RB5009, and this screenshot was taken last night when I was making these slides. And as you can see, at 21:55 last night, the new production version, which I have here, has actually been stable with no link flaps for the last 3 days. So we didn't actually screw up the hardware design. It was just a MikroTik bug. Yay. Cool. So marketing is easy, scaling is hard. So we've got a reasonable Twitter following for this project at this point. I'm semi-active in some Facebook groups around Starlink. Every time I put up a post, it gets potentially 30,000 eyeballs on it, and I normally get 100 plus comments and a bunch of likes. So marketing isn't really a problem. Scaling is a problem. The biggest challenge I have is sourcing the PoE magnetics, so the main module, the most expensive component. It turns out because these are quite specific and quite niche and not part of any real non-standard right now, they're not manufactured in huge quantities. So they're made in Shenzhen for Coilcraft, but then they don't actually warehouse them there, they don't keep them there. They ship them back to the US to Coilcraft's global warehouse. When they come through the US, thanks to the Orange Baby and Section 301 tariffs, they of course attract tariffs in the US for anything that's made in China. We then have to buy them off Coilcraft in the US and pay DHL to ship the made in China product that we've just paid tariffs on back to China. When it turns up in China, we then have to pay we have to pay a sales tax, which is either 13 or 17%, but it's not insignificant, and we have to pay, you know, customs loading fees, etc. And so the net result of that is our $10 US component costs something like $14 US. Other challenges that I've had, setting up shipping and logistics is hard. This component weighs 37 grams. DHL's minimum kind of ship weight is about 1 kg, and if you're selling these to people worldwide, you don't want to pay more in shipping than the product costs to make. Thankfully, if you spend half an hour on the phone to your DHL rep and you berate them repeatedly, they may eventually come back and give you better pricing. And we've now got significantly better pricing out of New Zealand, which means that for at least the first run, rather than having to go through the hassle of setting up a third-party logistics network, we should just be able to ship the first production run out of New Zealand on DHL direct to consumer. Again, other things, sales, pre-order channels, getting a Shopify, managing all of that, managing all the leads and inquiries, meeting customer demand, and of course, production runs and lead time. It's definitely something against you when you're manufacturing hardware. Every time you want to turn around a design, it takes about a month. And then if you actually want to save money on your design and get that component cost down, then your lead times push out to months and months, but also the market wants the product now. So yeah, there's plenty of kind of challenges when you're actually going to manufacture stuff. I mean, you know, we all know about the chip shortages, right? We've made a board, we've got some interest. So we decided to put up like a, not pre-orders, but essentially get yourself on a wait list. I think I put up the wait list quite late on a Sunday night, and when I woke up on Monday morning, 85 people had filled it out. We've now got about 120 different people on our wait list who want units, and we've got about 300 units waitlisted at the moment. I do have 100 units of the first production run actually in manufacturing right now. And because the component sourcing is so painful and it's the slowest part of the process, so making the PCB board normally only takes maybe 2 days, assembling it only takes a day, waiting for the components to come in takes 2 or 3 weeks. So I've sourced components for 200 boards, but we're only manufacturing 100, and then when we need to do our second production run, it'll only take a few days rather than, you know, taking another month. So where are these going? What are the use cases? Use cases where customers want them, off-grid solar setups, that's a big one. Obviously, if you've got a 12 volt or 24 volt or whatever off-grid system, and you're then taking the 12 volts into an inverter, pushing it up to 240, then into the Starlink injector, and then pushing it back down to 48, you have heaps of inefficiency there. So if you can either just go purely 48 volts DC, or you can just use something like a buck boost and just step it up from 12 volts to 48 volts, then you can gain a huge amount of efficiency. And so for people who are on off-grid setups, that's really meaningful. You have to put up less solar panels, you have to buy less batteries, so there's a really big use case there. Another market that have reached out is kind of mining industry or ice road truckers. So, you know, those kind of industries that are based in really remote locations that are already using satellite internet, they're interested in these. Starlink in the last, I think it's month or so, they've turned on roaming. So you pay them an extra $40 a month, and now you can take Dishy Portable. So in America, RVs are huge. Heaps of people want them for RVs to run off their 12 volt setups. Quite a few people have inquired about using them on their boats, and as you can see from the picture, also Priuses. The other kind of unexpected but logical market is civil defence and disaster recovery. One of our prototypes is down in Queenstown, and some of the locals there are looking at integrating into one of their civil defence kits. And that kind of makes sense. You know, you can jump out of a helicopter into a disaster zone where there's been an earthquake or a mudslide or a bridge is washed out, bring some batteries, plug in your Starlink, and you're off and running. So yeah, civil defence and DR is probably one of the unexpected markets that these will probably go to. And also lots of random edge cases. So they had one chap reach out to me who's doing remote edge compute, and he wants a board so that he can go from Starlink directly into his NVIDIA Jetson, and then he's doing like remote AI camera recognition stuff. So all sorts of cool and interesting you know, remote edge compute cases that Starlink opens up where you would want, you know, a DC power injector. So conclusions, hardware is easy, scaling, all of the other shit, sales, marketing, well, not so much marketing, but sales, logistics, component sourcing, that's what's really hard. Still don't have a house, but we have really fast internet. And we've now got Starlink, 4G, fixed wireless now, and also a second Starlink has just turned up because I need to test on Square Dishy. And I'm not quite finished yet, 2 more slides. So if you came to this talk and you thought we're going to be talking about actual hacking of Starlink, sorry, that wasn't what this talk was about, but if you actually want to follow a really cool hacker, go follow Oleg. He's pulling these things apart, he's spectrum analyzing them, he's pulled off the TPM module, he's dumped all the crypto keys. He's an actual hacker who's doing actual cool hacking things. So follow him, he's cool. And yeah, that's my talk on my adventures into hardware hacking.
Any questions for Liam?
Down the back. Right behind the
So I kind of missed a point, I think. So is the only way to get power into the Starlink dish via their proprietary PoE currently?
Correct. You can only use their proprietary PoE injector, which is mains only.
Because the first thing that I went was, why didn't you just run a pair of copper cables to it from a DC source?
Well, that's exactly what we're doing. We've got a Meanwell 48-volt injector down the hill, and we're running 48.
But I mean, like literally, why are you using RJ45 cable and a UDP to run that? Why don't you just run a peer next to it, and not have to deal with the PoE standard? Like if you just ran, I mean, in your particular case, we were up a hill. Why don't you just account for the voltage drop and run a pair of copper up and to the dish and just tap into it?
You mean as in like?
But But I didn't realize that you can only get it powered by PoE. That was the part that I was missing.
Yeah, sorry. So Dishy version 1 and version 2, they're not connectorized at all. So the PoE is, you know, like injection molded into the case. There is no external power injector. In Dishy version 3, they have connectorized it. But the way they've connectorized it is they've come up with a connector that's not quite USB-C and it's not quite mini HDMI. It's custom pin count, proprietary size, and only works with their equipment. So yeah, they want to keep that proprietary. They don't want you providing your own power. But also they have very good reason to do that because they don't want people who don't know what they're doing creating support nightmares for them.
Sorry, very quick question. How tolerant is the voltage input on Dishy? Does it matter which one you have, whether it's round or square? And are you considering adding a buck boost on the input for the next hardware rev?
Yeah, so great question. We've seen circular Dishy, it is supplied at 56 volts DC stock. We've seen it run as low as 40 volts DC. My one that you see up on the hill there is running at about 52 volts. I'd say keep it above 52 volts for circular. For square Dishy, it does come stock at 48 volt DC, so I probably wouldn't overdrive that. So depending on which unit you want, you will want to tune your voltage for it. One of the large markets that we've seen is primarily people who want to run it off 12 volt. So the problem that you have with running off 12 volt is most buck boost converters are really an economical design designed down to a cost. When you put a RF load on them, quite often the RF load, because it's doing like TX and RX modulation, its load is really variable. And so quite often buck boost converters, when they're running radios, they have problems actually just like regulating the voltage, and you'll just hear them screaming. So what we've actually done is I've got a shipment from China of a number of different buck boost converters at the moment from what appears to be a reputable vendor. We're going to test those in the field, so actually have it running on a real Starlink, hook up some USB oscilloscopes to it, make sure it doesn't scream, make sure the power's stable. I'm trying to come up with something that's somewhere between $25 and $50 for power setup, because no one's going to go out and buy a $300 Meanwell to run this. So yes, that is coming. We're looking at either having some certified or recommended devices that can be purchased from like easily available vendors, or just bundling some ourselves, depending on whether we want to deal with the support side.
Okay, thank you very much, Liam.
Cool.
And that was NZNOG 2022. So thank you very much, everybody, for coming. We do it for the audience, so we're all very pleased to see you, and we're very pleased you've made it to the end, so congratulations. We will do this again next year, but we haven't made any decisions. So goodbye, and safe travels.